Hello there, and welcome to Science for Sleep, where curiosity slows down just enough to get comfortable, and big questions are explored at a pace that doesn't demand anything from you except a little quiet attention. Tonight, we're drifting toward a question that sounds simple at first, almost obvious, and yet the more you sit with it, the stranger it becomes. Venus is closer to Earth than Mars, so why are we going to Mars? Before we ease into that puzzle, let me ask you something gentle and small. Where are you listening from tonight? Are you wrapped in a blanket somewhere cool and dark? Is it early evening where you are? Or very late? Maybe the sky outside your window is already black, or maybe it still holds a faint blue glow, and what time is it in your corner of the world right now? There's something quietly fitting about asking that while we talk about planets, because even though we're scattered across continents and time zones, we're all under the same sky. If this slow journey into space feels calming or quietly interesting, I'd be ever so grateful if you gave the video a like, maybe subscribed, and shared this little corner of thoughtful wandering with someone else who might need a soft landing at the end of their day. It helps this calm orbit continue. Now, let's step outside, at least in our minds. Imagine looking up just after sunset. The air is cooling. The world is shifting from busy to hushed, and there, low on the horizon, brighter than any star, almost steady, almost watchful, hangs a point of light, not twinkling like the others, not faint or shy, bold, clear, almost suspiciously bright. That's Venus. For thousands of years, long before telescopes and rocket engines, humans noticed that light. Ancient observers tracked it carefully. Sometimes it appeared in the morning before sunrise. Other times, it lingered after sunset. It became known as the morning star or the evening star, though of course it isn't a star at all, it's a planet. Our nearest planetary neighbour, at least on average. Closer than Mars. That's where the puzzle begins to take shape. If you ask someone casually, which planet should humans go to next? The answer you'll hear most often is Mars, the red planet, the dusty frontier, the one with rovers crawling across its surface and plans for human footprints sometime in the coming decades. Mars feels like the destination, Venus feels like background scenery. But strictly speaking, if we're talking about distance, Venus is often the closer world. At its nearest approach, Venus comes closer to Earth than Mars ever does. In fact, over long periods of time, Venus is statistically the planet that spends the most time closest to Earth. Not Mars, not even Mercury. Venus. So if space travel is hard and distance matters, and fuel is precious, why aren't we pouring all our energy into visiting the planet that's right next door? The answer isn't just about miles or kilometers, it's about temperature, pressure, atmospheres, engineering limits, human psychology, and the quiet reality that closer doesn't always mean easier. But we'll get there gently. For a long time, Venus seemed like a dream. In the early days of astronomy, when telescopes first began revealing that planets were worlds in their own right, Venus was especially intriguing. It's nearly the same size as Earth. Slightly smaller, yes, but close enough to be called a twin. Its gravity isn't wildly different. Its mass isn't alien. Its orbit sits just inside ours, still within the general neighbourhood of the Sun's warmth. Two rocky planets, similar size, similar bulk composition, orbiting the same star. It didn't seem unreasonable to imagine that Venus might be something like Earth, only a little warmer, perhaps tropical, perhaps covered in oceans hidden beneath those thick clouds, perhaps even alive. Those clouds were part of the mystery. Through early telescopes, Venus appeared smooth, bright, featureless. No continents, no craters, just a glowing white sphere. It reflected sunlight incredibly well, which is part of why it shines so brightly in our sky. Its cloud layer is thick and highly reflective, bouncing much of the sun's light back into space. If you were an astronomer in the early 20th century, peering at Venus without the benefit of spacecraft data, it would have been easy to imagine something lush beneath those clouds. Maybe a warm, misty world, maybe shallow seas, maybe thick jungles. The clouds could have been water vapour, the brightness could have meant oceans. Meanwhile, Mars looked cold and distant, red, dry, scarred. If you were placing bets on which neighbouring planet might resemble Earth, Venus would have seemed like the safer guess. And yet, as we began to send probes outward in the 20th century, the story changed. The first spacecraft that flew past Venus began to measure its atmosphere. The data came back quietly at first, almost unbelievable. The atmosphere wasn't mostly nitrogen and oxygen like Earth's. It wasn't even mostly water vapour. It was carbon dioxide, extremely dense carbon dioxide, and the temperature readings were not tropical. They were staggering. Surface temperatures on Venus average around 465 degrees Celsius, or about 870 degrees Fahrenheit, hot enough to melt lead. Hot enough that any conventional spacecraft electronics begin to fail quickly. Hot enough that a human presence on the surface, even in a highly engineered suit, becomes almost unthinkable with current technology, and that's just the heat. The pressure at the surface of Venus is about 92 times that of Earth's sea level pressure. It's roughly equivalent to being nearly a kilometre underwater in Earth's oceans. Imagine the weight of the atmosphere itself pressing down on you with that force. Any lander that touches the surface must survive not only extreme heat, but crushing pressure. The clouds that once suggested water turned out to be made primarily of sulfuric acid droplets. Not gentle mist, not warm rain, acid. Suddenly, the nearest planet didn't look like a sister world. It looked like a warning. Mars, by comparison, is cold, very cold. Average surface temperatures hover around minus 60 degrees Celsius. Its atmosphere is thin, about 1% the pressure of Earth's. There is radiation risk, there are dust storms, there is no breathable air, but it is not 465 degrees. It is not 92 atmospheres of pressure. And cold, as engineers will tell you, is often easier to manage than extreme heat. You can insulate against cold. You can generate heat. You can build habitats and control internal temperature. It's difficult, yes, but it's within the realm of possibility. Extreme heat, especially sustained heat combined with high pressure and corrosive chemistry, is far more punishing on materials. Metals weaken, electronics degrade, cooling systems struggle because the environment itself is already hotter than most engineered components can tolerate. So when we say Venus is closer, we're speaking only of distance through space. We're not speaking of accessibility. Distance in space is measured in kilometers. Difficulty is measured in physics. There's also another layer to this story, and it has less to do with temperature and more to do with imagination. Mars has always stirred something in us. Even before we had spacecraft, we could see subtle markings on its surface through telescopes. In the late 19th century, some observers believed they saw canals, artificial structures, evidence of civilization. That interpretation turned out to be mistaken, but the idea stuck. Mars became the planet of stories, of dying worlds, of ancient life. Venus, by contrast, remained hidden behind clouds. You couldn't see its surface at all. It offered no visible terrain to spark speculation. It glowed, yes. It shone brilliantly, but it didn't reveal. And humans are drawn to landscapes, to horizons, to places we can picture. It's easier to imagine walking across a dusty red plain beneath a pale sky than it is to imagine descending into a furnace beneath acid clouds. There's also orbital mechanics to consider, though we'll explore that more fully as we continue. Getting to Venus is not simply a matter of pointing a rocket at the closer dot. Venus orbits closer to the Sun than Earth does. To reach it, a spacecraft must actually shed orbital energy, falling inward toward the Sun. That requires a different type of trajectory compared to travelling outward toward Mars. It's not necessarily harder in terms of raw energy, but it changes the mission profile. More importantly, landing and surviving are separate challenges entirely. Mars rovers have lasted years. Some are still operating, sending back images of rocky plains and distant hills. Venus landers, on the other hand, have survived on the surface for minutes to a couple of hours at most, before succumbing to the heat and pressure. The Soviet Venera missions in the 1970s and 1980s were engineering triumphs, capturing the first images from the surface of Venus. But even those hardened machines eventually failed under the relentless conditions. When you're planning long-term human exploration, you're not just thinking about reaching a planet, you're thinking about staying, building habitats, growing food, extracting resources, generating power. Mars offers frozen water in its soil and polar caps. Water can be split into hydrogen and oxygen for fuel and breathing. It can support agriculture inside protected habitats. The soil, though toxic in some respects, can potentially be processed. Venus's surface offers almost none of that. Any human habitat would need to float high in the atmosphere, where temperatures and pressures are more Earth-like, perhaps around 50 kilometers above the surface. There are serious proposals for floating cities in Venus's upper atmosphere, but those remain conceptual for now. So when we ask, why are we going to Mars instead of Venus? The answer unfolds slowly. Because proximity is only one variable. Because survivability matters. Because engineering constraints are real. Because the red desert is harsh, but not apocalyptic. Still, Venus is not forgotten. In recent years, scientific interest in Venus has begun to rise again. New missions are being planned to study its atmosphere, its geology, its history. There is a growing recognition that Venus may hold critical clues about climate evolution, runaway greenhouse effects, and the long-term stability of Earth-like planets. If Venus was once more temperate, if it once had oceans that later evaporated under intense greenhouse warming, then its history could teach us something profound about our own world. Mars may be the destination for footprints, Venus may be the cautionary tale, and somewhere between those two worlds lies the reason we choose one frontier over another. But before we move further outward, or inward, let's linger just a little longer with that bright light in the sky, the one that rises before dawn or glows after sunset, the one that ancient civilizations watched carefully, charting its movements long before we understood orbits. Venus is closer, it shines brighter, and yet we are setting our sights on Mars. That choice says something about us, about what we fear, about what we believe we can survive, and about the kinds of worlds we imagine ourselves inhabiting. At first glance, the choice seems almost unfair in its simplicity. Two rocky worlds circle the same sun as Earth. Both are relatively close. Both have been studied for decades. Both have sent back data that reshaped how we think about planets and habitability. And yet, when the conversation turns to human exploration, to long-term presence, to building something that lasts, one planet consistently rises to the top of the list, while the other quietly recedes into the background. Mars becomes the destination. Venus becomes the question mark. This isn't because Venus lacks importance, quite the opposite. Scientifically, Venus is one of the most fascinating planets in the solar system. It challenges assumptions. It complicates simple ideas about Earth-like worlds. It forces uncomfortable comparisons. But when it comes to choosing where humans might go, where machines might operate for years instead of hours, the decision narrows in a way that feels almost inevitable. Still, inevitability is often something we notice only in hindsight. If you rewind far enough before space probes, before atmospheric data, before landers were crushed or melted, the choice was not so clear. Venus and Mars both carried hopes, projections, and unanswered questions. They were not rivals exactly, but they were contenders for attention, resources, and imagination. And the question that quietly guided everything was not, which planet is closer, but which planet is possible. Possibility is a layered thing. It isn't just about physics, it's about engineering limits, biological needs, psychological comfort, and the slow accumulation of evidence that tells us where effort is likely to pay off. Mars, even in its bleakness, offers a kind of compromise. It is hostile but not immediately lethal in every dimension. Its surface is cold, yes, and dry, yes, and bathed in radiation due to its thin atmosphere. But those dangers are ones we already know how to mitigate, at least in theory. Insulation exists, shielding exists, controlled environments exist. We know how to build habitats that keep heat in, rather than trying to force heat out against an environment that wants to melt everything. Venus asks for something else entirely. On Venus, the environment does not merely challenge life as we know it, it overwhelms it. The surface temperature alone eliminates almost every material we commonly rely on. The pressure adds another layer of stress. The chemistry adds another. Even if you solve one problem, the others remain, pressing in from every direction. That difference shapes every decision. When engineers plan a Mars mission, they think in terms of years. Years of operation, years of power generation, years of gradual wear. They can imagine a rover climbing hills, drilling into soil, analysing rocks, and transmitting data day after day. They can imagine astronauts living inside pressurised habitats, stepping outside in protective suits, returning safely, repeating the cycle. When engineers plan a Venus mission, the timeline shrinks dramatically. Minutes, hours, if everything goes perfectly. The surface becomes a place to visit briefly, not to inhabit. The planet itself dictates the terms. This alone doesn't make Venus unworthy of attention, it makes it different. And difference matters when resources are limited and ambition must be focused. Mars also offers something subtler, something that doesn't show up easily in equations. It offers continuity. When we look at Mars, we see signs of a past that might have resembled Earth's. Dried riverbeds, ancient lake basins, minerals that form in the presence of water, polar ice caps that wax and wane with the seasons. These features suggest that Mars was once warmer, wetter, and potentially more hospitable. That matters because it gives Mars a narrative arc we recognise, a planet that started with promise and lost something along the way, a world that cooled, dried, and thinned, rather than overheated and collapsed into a runaway state. Venus, by contrast, seems to have crossed a threshold and never returned. Its history, though still under investigation, points toward a catastrophic shift. A planet that may have once had water, perhaps even oceans, but then entered a feedback loop that amplified heat until the system became self-sustaining and extreme. This difference shapes how we imagine intervention. On Mars, the idea of gradual change doesn't feel entirely absurd. You can talk about thickening the atmosphere, warming the surface, releasing trapped gases, introducing greenhouse effects deliberately rather than accidentally. These ideas remain speculative and controversial, but they exist within the realm of discussion. On Venus, reversing the process feels almost mythic. Cooling a planet blanketed in carbon dioxide with surface temperatures capable of melting metal requires energy on a scale that borders on fantasy. The planet is not just hot, it is structurally committed to being hot. That commitment matters when humans think long-term. There's also gravity to consider, not just in the physical sense but in the biological one. Mars has about 38% of Earth's gravity. That's low, but not zero. It's enough that humans can walk, work, and move in ways that still resemble life on Earth. It may not be ideal for long-term health, but it's something the body can respond to. Venus's gravity is much closer to Earth's, about 90%. That sounds promising until you realise that the only region where pressure and temperature are remotely tolerable is high in the atmosphere, far above the surface. Any long-term human presence would need to float, suspended in a dense, corrosive sky. Living in a balloon city is a fascinating idea, but it introduces complexities that go far beyond building structures on solid ground. Humans evolved on surfaces. We build cities anchored to land. We extract resources from soil and rock. Mars, despite its harshness, still offers ground. Venus's surface might as well be a mythological underworld as far as human habitation is concerned. There is also the matter of return. Mars missions are designed with round trips in mind. Even if a mission is long and risky, The idea of coming back remains central. Launching from Mars requires less energy than launching from Earth due to its lower gravity. That makes return scenarios at least theoretically manageable. Launching from Venus's surface would be far more difficult. The thick atmosphere that makes entry so destructive also makes ascent extremely demanding. Any vehicle would need to fight both gravity and immense atmospheric resistance. The engineering challenges stack quickly, so when planners sit down and ask, where does this lead? Mars offers pathways, Venus offers walls. But none of this fully explains why Mars captures the imagination the way it does. That part of the story lives somewhere between science and psychology. Mars looks like a place, not just a planet, but a landscape. We have images of hills, valleys, plains, sunsets tinted but familiar. We can imagine ourselves standing there, even if we know we can't yet. The sky may be pale and thin, the ground rusted, the air unbreathable, but the geometry feels legible. Venus hides its surface behind clouds so thick that even today, radar is required to map it. There are mountains and plains down there too, but they feel abstract, remote, detached from direct experience. It's harder to imagine being there because nothing about being there resembles anything in our evolutionary memory. Humans are visual thinkers. We respond to scenery. Mars gives us scenery. That matters more than we often admit. When a planet becomes a symbol, it shapes funding, public interest, and long-term commitment. Mars has become a symbol of endurance, exploration, and second chances. Venus has become a symbol of excess, warning, and loss of balance. Neither symbol is entirely fair, but both are powerful. Mars is not kind. It will not welcome us. It will expose us to radiation, isolate us psychologically, and challenge every system we depend on, but it does so in ways we can imagine managing. Venus does not negotiate. It does not offer margins. So the choice between two planets becomes less about distance and more about gradients. How steep is the slope from survival to failure? How many layers of protection are required? How much redundancy is possible? How much time do you have to fix a problem before it becomes fatal? Mars gives you time. Venus takes it away. And yet, Venus keeps calling quietly from the sky, brighter than Mars ever appears. It reminds us that proximity does not guarantee suitability, that similarity in size does not imply similarity in fate, that planets, like stories, can diverge dramatically from the same opening chapter. If you step outside on a clear evening and give your eyes a moment to adjust, there is a good chance your attention will be drawn almost immediately to a single point of light. It doesn't flicker the way stars do. It doesn't hide among constellations. It simply announces itself steady and bright, as if it knows it will be noticed. For many people, this moment happens without any prior interest in astronomy at all. You don't need to know where to look. Venus finds you. This brightness is not subtle. After the moon, Venus is the brightest natural object in the night sky. It can cast faint shadows. It can be seen even from cities where most stars are washed away by artificial light. It hangs low near the horizon after sunset, or rises ahead of the sun before dawn, depending on where it is in its orbit, and it does so with a kind of quiet confidence. Long before rockets and radar, humans noticed this. Ancient people did not need instruments to mark Venus as something special. Its brilliance set it apart immediately. While stars shifted slowly across the sky night after night, Venus wandered. It appeared, disappeared, returned. Sometimes it rose in the east before the sun, earning the title of morning star. Other times it followed the sun down, glowing softly in the west as the evening star. For a long time, many cultures believed these were two separate objects, one that greeted the day, one that closed it. It took careful observation, patience, and the slow accumulation of the knowledge to realize they were the same planet, tracing a predictable but unfamiliar path. That wandering mattered. In a sky where most lights were fixed, Venus moved. It defied the background. It demanded explanation. The brightness itself comes from a combination of factors, none of which involve Venus generating light of its own. It is not glowing, it is reflecting, and it does so exceptionally well. Venus is wrapped in a thick blanket of clouds that reflect about 70% of the sunlight that hits them. This reflectivity, combined with its relative proximity to Earth, is what makes Venus so striking. Mars, by contrast, reflects far less sunlight. Its surface is darker, its atmosphere thinner, its presence more subdued. Even when Mars is relatively close to Earth, it rarely dominates the sky the way Venus does. Mars glows red but softly. Venus shines white and unapologetic. There is something psychologically important about that difference. Brightness draws attention. It creates familiarity. Venus has always been present in human awareness, even for people who never study the sky formally. It marked time. It marked seasons. It became woven into stories, calendars, and rituals. It was associated with gods, goddesses, love, war, fertility, death, rebirth. Cultures separated by oceans and centuries all singled it out. This makes it even more interesting that Venus, for all its visibility, did not become the focus of our future plans in the same way Mars did. The planet that announces itself nightly feels less like a destination and more like a symbol. It is close enough to watch, but not close enough to imagine touching. That distinction didn't exist at first. Before the space age, brightness suggested promise. If a planet reflected that much light, if it was that large in our sky, if it was that similar in size to Earth, then surely it must be worth visiting. Surely it must be approachable. Surely it must hold something familiar beneath those clouds. Brightness became projection. In the early 20th century, some scientists speculated openly about life on Venus. The thick atmosphere was interpreted not as a threat, but as protection. Clouds might mean rain. Rain might mean rivers. Rivers might mean vegetation. And vegetation might mean ecosystems. The logic wasn't foolish given the information available at the time. Earth itself is a cloud-covered planet from a distance. Without careful instruments, it would be easy to mistake Venus for something similar. Mars, despite all its later fame, looked less inviting then. It was dimmer, colder. Its polar caps were visible, but that only emphasized its harshness. Venus, glowing softly and consistently, felt alive in a way Mars did not. The brightness of Venus also made it easier to study with early telescopes, though not in the way people hoped. Even with magnification, the surface remained hidden. The clouds were relentless. No matter how powerful the telescope became, Venus refused to reveal its face. This led to a strange paradox. Venus was the most visible planet, yet the least visually understood. Mars, though dimmer, allowed glimpses of surface features. You could track dust storms. You could map polar ice. You could convince yourself you were seeing structure, even if that confidence sometimes went too far. Venus offered only light and mystery. That mystery lingered well into the mid-20th century. When radio astronomy and spectroscopy began to advance, scientists started measuring Venus's temperature remotely. Early readings were confusing and contradictory. Some suggested moderate warmth, others hinted at extreme heat. The uncertainty allowed hope to survive longer than it probably should have. Brightness again played a role. A planet that bright could not easily be imagined as dead or hostile. It felt counterintuitive. Human intuition is not well calibrated for planetary physics. We associate brightness with warmth, but also with comfort, with presence, with life. The truth, when it arrived, was jarring precisely because it contradicted that instinct. When spacecraft finally approached Venus and sent back reliable data, the brightness took on a different meaning. The reflective clouds were not shielding a temperate surface. They were trapping heat. The same clouds that made Venus beautiful in the sky were part of the mechanism that turned it into the hottest planet in the solar system. brightness became a warning sign rather than an invitation. That shift mattered. It reframed Venus not as a place we misunderstood slightly, but as a place fundamentally misaligned with our expectations. The planet had lured us visually, only to reveal a reality that felt almost punitive by comparison. Mars did the opposite. It looked harsh from the beginning, and it largely lived up to that impression. There were disappointments, certainly. The canals were illusions, the civilizations were fiction, but the core image of a cold, dry world remained consistent. Mars did not betray expectation. Venus did. This difference affects how we relate to these planets emotionally even now. Venus is stunning to look at. Mars is not. Yet Mars feels approachable in a way Venus does not. That may sound irrational, but exploration has always been shaped by emotion as much as by data. We choose frontiers that feel challenging but not mocking. We respond to environments that appear difficult but comprehensible. Venus feels like a trap disguised as a jewel. There is also something about timing. Venus is most visible when the sky is changing, at dusk, at dawn, transitional moments. It accompanies shifts rather than anchors them. Mars, when it appears bright, often does so deep in the night sky, among the stars. It feels like part of the broader cosmic backdrop rather than a boundary marker. These subtle associations accumulate over time. They shape mythology, language, and eventually priorities. When humans began planning interplanetary missions, visibility alone was not enough to drive decision-making. Data replaced projection, and the data was clear. Venus's brightness was not a sign of hospitality. It was a symptom of an extreme atmospheric system. Still, Venus did not lose its scientific value. If anything, it gained a new kind of importance. The same runaway greenhouse effect that makes Venus unlivable also makes it a natural laboratory for understanding climate processes. By studying why Venus became what it is, scientists can better understand the delicate balance that keeps Earth temperate. Brightness, in this context, becomes ironic. Venus shines as a reminder of what happens when feedback loops spiral beyond control. It is visible to everyone, every clear night, a planetary caution sign written in light. Mars does not offer that lesson as directly. Its problems are different. Its failures are quieter. Its atmosphere thinned rather than thickened. Its water escaped rather than boiled. It cooled instead of overheated. That narrative feels less immediately threatening and perhaps more forgiving. Brightness, then, becomes part of why Venus is not our chosen destination. Not because it fails to inspire, but because it inspires a different response. It asks questions rather than offering footholds, and yet every night it returns, steady, bright, impossible to ignore entirely. As we move forward, the contrast will sharpen further. Visibility versus viability, nearness versus navigability, beauty versus tolerance. The sky gives us clues, but it does not make decisions for us. Venus will continue to shine, unchanged by our choices. Mars will continue to wait, dusty and quiet, marked by the slow tracks of machines that move one careful meter at a time. The brightest object in the night does not always mark the path forward. Sometimes it simply illuminates the question we are still learning how to answer. There was a time when Venus did not look like a cautionary tale, not in the sky and not in the mind. Before probes, before pressure readings, before melted landers and crushed instruments, Venus occupied a very different place in scientific imagination. It wasn't the planet of acid clouds and crushing heat yet. It was something far more familiar, something almost comforting, an Earth-like world. This idea didn't come from fantasy alone. It came from reasonable assumptions built on limited information. Venus and Earth are remarkably similar in size. Their diameters differ by only a few hundred kilometers. Their masses are close enough that gravity on Venus would feel only slightly lighter than what we're used to. Their internal compositions, as far as we can tell, are broadly similar, both rocky planets with metallic cores and silicate mantles. When early astronomers grouped the planets, Venus and Earth naturally fell together. They were the twins. Mars was smaller, lighter, more obviously different. Mercury was extreme. The gas giants were another category entirely. Venus sat right there, next to Earth, close in size, close in orbit, wrapped in clouds that hid its details but hinted at complexity. If you didn't know any better, you might have assumed Venus was simply Earth, with the thermostat turned up a little. And for a long time, that assumption wasn't obviously wrong. In the late 19th and early 20th centuries, scientific understanding of planetary atmospheres was still developing. Spectroscopy existed, but its interpretations were limited. Telescopes could not penetrate Venus's clouds. Radio observations were in their infancy. What scientists saw was brightness, size, and mystery. Those clouds became the foundation for speculation. Clouds on Earth mean water. Water means weather. Weather implies cycles. Cycles suggest stability. And stability is where life takes root. It wasn't unreasonable to imagine Venus as a warm, humid world, perhaps covered in shallow seas, endless swamps, or dense vegetation. Some even pictured rain falling continuously beneath a perpetually overcast sky. Science fiction embraced this version eagerly. Venus became a setting for stories about tropical planets, dangerous jungles, and strange but thriving ecosystems. These weren't wild guesses pulled from nowhere. They were extrapolations based on the idea that planets of similar size and composition, orbiting the same star, might follow similar evolutionary paths. Earth's path felt natural. Venus's path was assumed to be parallel. Mars, again, suffered by comparison. Its thin atmosphere and visible surface features suggested dryness. Venus's hidden surface allowed optimism to survive longer. When you cannot see a problem, it's easier to imagine that none exists. Even as technology improved, Venus resisted clarity. Radar mapping had not yet matured. Early temperature estimates conflicted. Some readings suggested mild warmth. Others hinted at extremes. The scientific community debated fiercely. There was no consensus. What kept the twin narrative alive was the lack of a definitive contradiction. That changed abruptly in the mid-20th century. As spacecraft began venturing beyond Earth, Venus became one of the first major targets. Its proximity made it accessible. Its mystery made it irresistible. If any planet could confirm the idea that Earth-like worlds were common, Venus seemed like the best candidate. The first flybys delivered unsettling news. Measurements of Venus's atmosphere revealed its composition with increasing precision. Carbon dioxide dominated, not just present, but overwhelming. Nitrogen existed too, but oxygen was scarce. Water vapor, which many hoped would be abundant, was present only in trace amounts. Then came the temperature data. The surface was not warm, it was blistering. What shocked scientists wasn't just the number itself, but the uniformity. Venus was hot everywhere. Dayside, nightside, equator, poles. There was no escape from the heat. The thick atmosphere circulated energy efficiently, erasing temperature differences that might have provided pockets of relief. This was not a tropical Earth. This was something else entirely. The twin narrative collapsed quickly once the data became undeniable. But it left behind a more complex and interesting question. How did two planets that started so similarly end up so different? That question reshaped planetary science. The leading explanation centers on what's known as a runaway greenhouse effect. Earth experiences a greenhouse effect too. It's what keeps our planet warm enough to support life. Gases like carbon dioxide and water vapor trap heat, preventing it from escaping entirely into space. Without this effect, Earth would be frozen. Venus appears to have taken this same process and pushed it beyond a critical threshold. Early in its history, Venus may indeed have had significant amounts of water. Some models suggest it could have had oceans. Being closer to the Sun, Venus received more solar energy than Earth. That extra heat would have increased evaporation. More water vapor in the atmosphere would have trapped more heat. More heat would have caused more evaporation. A feedback loop. Eventually, the process would have accelerated uncontrollably. Water vapor, itself a powerful greenhouse gas, would have filled the atmosphere. Temperatures would have risen high enough to prevent liquid water from existing on the surface at all. Ultraviolet radiation from the Sun would have broken water molecules apart in the upper atmosphere, allowing hydrogen to escape into space. Once the water was gone, there was no easy way back. Carbon dioxide, released from volcanic activity, would have accumulated without being absorbed by oceans or locked away in carbonate rocks. On Earth, plate tectonics and liquid water help regulate atmospheric carbon dioxide over long timescales. Venus lacks both of these stabilizing systems. The result was a planet locked into an extreme state, its atmosphere thick, its surface hot, its past erased beneath pressure and heat. Understanding this history transformed Venus from a failed Earth into a cautionary parallel. It wasn't simply unlucky, it followed the same physical laws as Earth, but crossed a boundary that Earth, so far, has not. That realization made Venus far more relevant, not less. But relevance does not equal suitability. From the perspective of human exploration, the twin idea died hard. Emotionally it lingered. Venus looks like it should be friendly. It's almost the same size. Its gravity feels right. It shines beautifully. It feels unfair that it is so hostile. Mars does not create that same sense of betrayal. It looks barren and behaves accordingly. Venus looks inviting and punishes curiosity. This emotional mismatch matters more than we like to admit. When humans explore, we don't just calculate risk, we assess trust. Mars feels like a difficult partner. Venus feels like a trickster. Even today, when scientists discuss Venus's past, the language reflects loss. A world that could have been. A twin that took a different path. A reminder that similarity at birth does not guarantee similarity in outcome. Mars, for all its differences, feels honest. What you see is what you get. There is also the question of time. If Venus was once Earth-like, that window appears to have closed very early in the solar system's history. By the time life was gaining a foothold on Earth, Venus may already have been too hot. Mars, on the other hand, seems to have remained potentially habitable for longer, perhaps hundreds of millions of years. That duration matters when thinking about life, but it also matters when thinking about stability. A planet that changes slowly is easier to plan around than one that tips abruptly into extremes. Venus teaches us that planetary systems can flip states irreversibly. Mars teaches us that they can fade gradually. So when we talk about Venus as Earth's twin, we're not invoking nostalgia. We're acknowledging a shared starting point and divergent destinies. That divergence is precisely why Venus is studied intensely, even if it is not chosen as a destination for humans. Mars becomes the practical sibling. Venus becomes the reminder. And that distinction feeds directly into the larger question of why we go, where we go. Exploration is not only about curiosity, it is about continuity, about choosing paths that allow learning to build on itself rather than resetting with every step. Venus's past may resemble Earth's, its present does not. Mars's present is harsh, but its trajectory feels incomplete rather than closed. For decades, Venus kept its secrets intact. No matter how carefully astronomers watched, no matter how powerful the telescopes became, the planet remained wrapped in an unbroken veil. The clouds did not thin, they did not part, they did not hint at what lay beneath. From Earth, Venus was all atmosphere and brightness, a smooth disk without scars or features, offering no visual clues about its surface at all. That persistent opacity did something subtle to human thinking. It delayed certainty. It allowed hope and speculation to coexist with doubt far longer than they otherwise might have. As long as the clouds remained closed, no single idea could fully defeat the others. Venus could still be many things at once. Then came the day when we stopped relying on light alone. The first spacecraft sent toward Venus were not designed to see in the traditional sense. They were designed to measure, to sample, to listen to signals that human senses could not detect. Radio waves, pressure readings, temperature profiles, chemical signatures. These were the tools that would finally bypass the visual barrier and tell us what the clouds were hiding. What they revealed was not a gentle clarification, but a shock. Early flybys in the late 1950s and early 1960s began returning data that immediately unsettled researchers. Radio observations suggested temperatures far higher than anyone had confidently predicted. At first, some dismissed the readings as artifacts, distortions caused by Venus's thick atmosphere interfering with measurements. The idea that an Earth-sized planet could be hotter than Mercury, which orbits much closer to the Sun, seemed absurd. But the numbers kept coming back the same. Each mission refined the picture, each pass added detail. The surface temperature was not just warm, it was uniformly extreme. And the heat did not fade on the night side of the planet, as it would on a world with a thin atmosphere. Venus's atmosphere was redistributing energy so efficiently that day and night barely mattered. This alone suggested something profound was at work. As probes began to sample the atmosphere directly, the composition became clear. Carbon dioxide dominated. Nitrogen was present, but oxygen was almost absent. Water vapor existed only in trace amounts. The clouds, once imagined as rain-bearing and life-supporting, turned out to be composed largely of sulfuric acid droplets. Sulfuric acid, not mist, not vapor. Acid suspended in a dense, choking sky. This discovery redefined the clouds entirely. They were no longer a sign of protection or fertility. They were part of the mechanism that trapped heat and sealed Venus into its extreme state. The brightness that made Venus so beautiful from Earth was now understood as a reflection from a hostile chemical shield. Still, there was one more barrier between understanding and certainty. The surface itself. For all the data collected during flybys, the surface remained theoretical until something could touch it. Landing on Venus was not a trivial challenge. Any spacecraft would have to survive a descent through crushing pressure, violent winds and corrosive chemistry, only to arrive in an environment hot enough to destroy electronics rapidly. Yet attempts were made. In the 1960s and 1970s, a series of landers were sent toward Venus, most famously by the Soviet space program. These missions were designed with an acceptance of sacrifice built in. No one expected long lifespans. The goal was not endurance, but contact. When the first successful lander transmitted data from the surface, it confirmed what many already feared. The pressure was immense, the temperature was unforgiving, the environment was utterly incompatible with anything resembling human survival, and yet, the most emotionally powerful moment came not from numbers but from images. Eventually cameras sent back photographs. They were grainy, low resolution, limited in scope, but they showed a real surface, rocks, flat plains, a yellowish, dimly lit landscape under a dense sky. There were no oceans, no vegetation, no movement, just a barren, baked terrain that looked less like a lost paradise and more like a geological punishment. That was the day the clouds truly opened, not because they physically parted, but because the illusion they sustained finally collapsed. Venus was no longer unknowable, it was known, and the knowledge was irreversible. The reaction within the scientific community was swift and sobering. Decades of speculation were replaced with a single, consistent narrative. Venus was not an Earth-like world gone slightly wrong. It was a planet that had undergone a catastrophic transformation, locking itself into a state from which there was no easy escape. This forced a re-examination of assumptions that extended far beyond Venus itself. If two planets could start with similar ingredients and end in radically different conditions, then habitability was not guaranteed by size, distance, or composition alone. Stability mattered. Feedback loops mattered. Small differences early on could cascade into planetary scale consequences. Venus became a test case. The day the clouds opened marked a turning point not only in how we saw Venus, but in how we thought about planets in general. It introduced a new caution into the search for Earth-like worlds. Similarity was no longer enough. Context was everything. Mars benefited indirectly from this shift. While Venus revealed how bad things could get, Mars revealed how quiet decline could look. Its atmosphere thinned. Its water froze or escaped. Its magnetic field faded. But it did not trap itself in an irreversible furnace. Mars became a study in loss without collapse. The contrast sharpened priorities. From an engineering perspective, Venus's surface became almost irrelevant for long-term missions. It was simply too extreme. Research shifted toward orbiters, atmospheric probes and brief landers designed to gather data quickly before failing. No one seriously discussed surface bases or extended human activity there anymore. Mars, meanwhile, became the focus of increasingly ambitious planning. Rovers were designed for longevity, landers were upgraded, orbiters mapped resources. The idea of human presence, while still distant, became something people could outline with rough timelines and technologies. This divergence was not ideological, it was practical. The data forced it. Even so, Venus did not lose its scientific importance. In some ways, it gained it. The very extremity that made Venus unsuitable for humans made it invaluable as a natural experiment. It showed what happens when greenhouse effects run unchecked. It showed how planetary systems can cross tipping points. It showed how atmospheres can become prisons rather than blankets. These lessons became especially relevant as Earth's own climate entered discussions of change and stability. Venus was no longer just another planet. It was a reference point, a reminder that planetary climates are not static, and that feedbacks do not negotiate. But from the standpoint of exploration, the door closed decisively. The day the clouds opened was the day Venus ceased to be a candidate for familiarity. It became alien in a way that Mars never quite did. Mars may be hostile, but it is a hostility we recognize. Venus's hostility feels absolute. That perception shapes not only mission planning, but cultural narrative. After the data, Venus faded from science fiction as a setting for adventure and settlement. It remained as a backdrop for cautionary tales or speculative floating habitats, but no longer as a place where humans could walk freely, even in imagination. Mars, by contrast, became more real, more grounded, more tangible. There is an irony here that is difficult to ignore. Venus hid its truth behind clouds that reflected light beautifully. Mars displayed its barrenness openly. One misled by concealment, the other warned by exposure. Humans, it seems, prefer honest hardship to hidden catastrophe. The opening of Venus's clouds also marked a psychological shift in how we define closeness. Distance stopped being measured solely in kilometers. Environmental compatibility became the real metric. A planet could be nearby in space and impossibly far in practice. That idea would shape every future discussion about where to send people, where to invest resources, and where to imagine a future beyond Earth. Yet the story does not end with disillusionment. Knowing what Venus is allows us to ask better questions. How long did it take to reach this state? Were there intermediate phases that might still be observable in its geology? Could microbial life ever have existed in its clouds, where temperatures are milder? Are there lessons in its past that we have not yet extracted? These questions remain open, and they keep Venus firmly within the scope of exploration. Even if the form that exploration takes is fundamentally different from Mars, the clouds opened, but they did not empty the planet of meaning. They transformed it. If there is one phrase that captures the reality of Venus more accurately than any dramatic headline, it is this: the sky itself is the danger. not the ground beneath your feet, not the horizon, not even the distance from the sun. On Venus, the atmosphere is not a backdrop. It is the dominant feature of the planet, an active, overwhelming force that shapes everything beneath it. On Earth, we live at the bottom of an ocean of air, but we rarely notice it. The pressure is gentle enough that our bodies evolve to balance it without effort. We walk, breathe, sleep, and think without feeling the weight of the sky above us. It presses down, yes, but so evenly and mildly that it becomes invisible. On Venus, the sky does not disappear into the background. At the surface of Venus, the atmospheric pressure is about 92 times greater than Earth's sea level pressure. That number is abstract until you translate it into something familiar. It is roughly the pressure you would experience nearly 1 kilometre beneath the surface of Earth's oceans. Imagine standing on the seafloor at that depth, with water pressing in from all sides, pushing against every surface of your body. Now replace the water with air. This is not a gentle squeeze, it is a constant crushing force. Every square centimetre of surface is under stress. Any structure, any machine, any material exposed to it must be built not just to exist, but to resist collapse at all times. This pressure is not an accident. It is the natural consequence of Venus's massive atmosphere. The planet's air column is thick, dense and heavy, composed mostly of carbon dioxide. While Earth's atmosphere thins rapidly with altitude, Venus's remains oppressive all the way down, piling its weight onto the surface below. If you were somehow able to stand on Venus without being immediately destroyed by heat, the pressure alone would feel disorienting. Your body would not function. Your lungs could not expand. Your blood chemistry would fail. Even specially designed pressure suits, the kind used for deep-sea exploration on Earth, would struggle to maintain integrity under such conditions, especially when combined with the heat. And the heat cannot be separated from the pressure. The two reinforce each other. At Venus's surface, temperatures hover around 465 degrees Celsius. That is hot enough to melt lead, deform steel, and destroy most electronics within minutes. Unlike Earth, where temperature varies widely between day and night, Venus maintains this heat almost uniformly. The thick atmosphere acts like a thermal blanket, trapping energy and redistributing it efficiently around the planet. This means there is no safe side, no cooler night, no polar refuge, no seasonal relief. The heat and pressure work together to create an environment that does not merely challenge survival, it eliminates it. This is why Venus landers are designed with an acceptance of failure. Engineers know from the start that time on the surface will be measured in minutes or hours, not days or years. The goal is to gather data quickly before the environment overwhelms the systems. When the Soviet Venera landers touched down on Venus, they became the first human-made objects to operate on the surface of another planet. This achievement is often overshadowed by later missions to Mars, but it remains one of the most extreme engineering feats ever attempted. These landers were built with thick pressure vessels, robust insulation, and minimal moving parts. Even so, their operational lifespans were brutally short. They transmitted images and measurements for a brief window, then fell silent. The crushing sky won. Pressure also changes the behavior of materials in ways that are difficult to predict. Metals deform, seals fail, lubricants break down, electronic components overheat and short-circuit. Cooling systems become nearly useless because there is no temperature gradient to exploit. You cannot radiate heat away efficiently when the surrounding environment is hotter than the system you're trying to protect. On Mars, by contrast, the problem is often the opposite. The atmosphere is so thin that heat escapes too easily. Machines must be protected from cold. Habitats must be insulated to retain warmth. But these are challenges we know how to approach. Cold can be countered with energy. Pressure can be supplied artificially inside structures. On Venus, pressure must be resisted constantly. It is always trying to crush inward. This difference alone explains much of why Venus is not considered a viable surface destination for humans. But the sky has more ways to make its presence felt. Venus's atmosphere is not just dense, it is dynamic. Winds in the upper atmosphere reach speeds of hundreds of kilometers per hour. The planet exhibits a phenomenon known as superrotation, where the atmosphere circles the planet far faster than the planet itself rotates. While Venus takes about 243 Earth days to complete one rotation, its atmosphere can circle the planet in just a few days. This creates extreme wind shear and turbulence in the upper layers. Near the surface, winds are slower due to friction, but they are still capable of transporting heat and chemicals efficiently. The atmosphere behaves like a massive heat engine, distributing energy with relentless consistency. Then there is the chemistry. The clouds of Venus are composed primarily of sulfuric acid droplets. This acid forms when sulfur dioxide, released by volcanic activity, reacts with water vapor in the atmosphere. While the water content is low, it is sufficient to produce vast, thick layers of acidic clouds. These clouds are corrosive, they attack metals, they degrade exposed surfaces. Any long-term structure in the Venusian atmosphere would need to resist not only pressure and heat, but constant chemical assault. Even if a human habitat were placed high in the atmosphere, where temperatures and pressures are closer to Earth-like conditions, the surrounding environment would still be hostile. Materials would need to be carefully selected, maintenance would be constant, failure would be unforgiving. The sky never rests. This leads to a deeper realization about Venus. The planet is not dangerous in isolated ways, it is dangerous systemically. Every aspect of its environment reinforces the others. Pressure amplifies heat. Heat accelerates chemical reactions. Chemistry degrades materials. Winds distribute energy and corrosive compounds. There is no single problem to solve. There is an entire system to contend with. Mars, again, presents a different picture. Its dangers are severe, but they are modular. Radiation can be shielded. Cold can be managed. Dust can be mitigated. Thin air can be replaced inside habitats. Each challenge can be addressed individually, even if the combined effort remains immense. Venus does not allow that kind of piecemeal approach. The environment operates as a unified force. This has implications not only for human exploration, but for robotic missions as well. Every component sent to Venus must be over-engineered relative to its Mars counterparts. Even then, mission durations are short. The return on investment, measured in operational time, is limited. This doesn't mean Venus is ignored. Orbiters and atmospheric probes continue to yield valuable data. Radar mapping has revealed a surface shaped by volcanism, vast plains and towering structures. There is evidence that Venus may still be geologically active, but the surface remains a place of brief visits, not prolonged study. The crushing skies dictate the terms. There is also a psychological dimension to this environment that is often overlooked. Humans do not just need physical safety. They need a sense of agency. On Mars, an astronaut can imagine stepping outside, planting tools, moving deliberately across terrain. Even in a pressurized suit, the ground offers stability. There is a horizon you can walk toward. On Venus, the idea of standing on the surface is almost meaningless. You would be pinned by the atmosphere, overwhelmed by heat, immobilized by pressure. The sky would dominate your awareness completely. There would be no sense of expansion, only containment. Even floating habitats, often proposed as a workaround, carry this psychological weight. Living in the sky of Venus would mean always knowing what lies below, an uninhabitable surface, a pressure and heat trap with no margin for error. A failure in buoyancy or structural integrity would not lead to a hard landing. It would lead to destruction. Mars, for all its dangers, allows for imagination to coexist with fear. Venus overwhelms imagination with inevitability. This distinction matters when societies decide where to invest long-term effort. Exploration is not just about what is technically possible. It is about what feels like it can be sustained, repaired, and adapted to over time. Venus resists adaptation. It is worth noting that none of this makes Venus uninteresting. In fact, it makes it uniquely valuable as a case study in planetary extremes. Understanding how Venus's atmosphere behaves under such conditions informs climate models, atmospheric physics, and even our understanding of exoplanets. Many planets discovered around other stars resemble Venus more than Earth or Mars. In that sense, Venus may be the more common planetary outcome. But common does not mean welcoming. The crushing skies of Venus serve as a constant reminder that habitability is fragile, that planets can tip into states that are stable but hostile, that once certain thresholds are crossed, the environment can lock itself into conditions that persist for billions of years. Mars crossed different thresholds. It lost its atmosphere rather than trapping too much of it. It cooled rather than overheated. It became quiet rather than oppressive. Those differences shape our choices, even if we don't always articulate them explicitly. Venus allows us to observe, to measure, to learn. Mars allows us to imagine staying. That difference, subtle at first, grows sharper the longer you sit with it, as the weight of Venus's atmosphere presses down not only on landers and probes, but on the very idea of calling that world anything other than what it is. A planet where the sky itself has become the dominant force, shaping every decision we make about where humanity might go next, and where it cannot, at least not yet, hope to linger. The story of Venus does not begin with fire. It begins quietly, with sunlight, water, and balance. The same basic ingredients that shaped Earth were present there too, orbiting the same star, forming from the same disk of gas and dust. For a time, Venus may have looked unremarkable in the grand scheme of planetary evolution. Warm? Yes. Slightly closer to the Sun? Yes. But not obviously doomed. The transformation that followed was not sudden in the way explosions are sudden. It was gradual, cumulative, and driven by feedback. The kind of process that does not announce itself clearly until it is already too late to stop. What happened on Venus is what scientists call a runaway greenhouse effect, and it stands as one of the clearest examples of how planetary systems can amplify small differences into irreversible outcomes. To understand this, it helps to begin with something familiar. Earth is warm because of its greenhouse effect. Without it, our planet would be a frozen world locked in ice. Sunlight reaches the surface, warms it, and the surface radiates heat back towards space. Greenhouse gases like carbon dioxide and water vapor trap some of that heat, slowing its escape and keeping temperatures within a range that allows liquid water to exist. This process is not inherently bad. It is necessary. The problem arises when the balance tips. Venus, being close to the Sun, received more solar energy from the beginning. That alone did not guarantee disaster, but it placed Venus closer to a critical threshold. A slightly warmer planet means more evaporation. More evaporation means more water vapor in the atmosphere. And water vapor is not just a passive participant. It is a powerful greenhouse gas in its own right. As Venus warmed, more water entered the atmosphere. As more water entered the atmosphere, more heat was trapped. As more heat was trapped, temperatures rose further, driving even more evaporation. This positive feedback loop reinforced itself. At first, the changes may have been subtle. Oceans may have warmed, clouds may have thickened, rainfall patterns may have intensified. But over time, the feedback gained momentum. Eventually, Venus crossed a line. Once surface temperatures rose high enough, liquid water could no longer exist stably. Oceans began to boil, not violently at first, but persistently. Water vapor filled the atmosphere, creating an even stronger greenhouse effect. At this stage, Venus's climate system became unstable in a fundamental way. The loss of liquid water was not just a symptom, it was a turning point. On Earth, liquid water plays a crucial role in regulating carbon dioxide. CO2 dissolves in oceans, reacts with rocks, and becomes locked away in carbonate minerals. This long-term carbon cycle acts as a thermostat, preventing extreme swings in atmospheric composition. Venus lost that mechanism. As water disappeared from the surface, carbon dioxide released by volcanic activity had nowhere to go. It accumulated in the atmosphere. As CO2 levels rose, so did temperatures. As temperatures rose, the last remaining traces of surface water vanished. The planet entered a self-sustaining state. But the story doesn't end there. High in Venus's atmosphere, ultraviolet radiation from the sun began to break apart water molecules. Hydrogen, being light, escaped into space. Oxygen, heavier, reacted with surface materials or was stripped away by solar wind over time. This process permanently depleted Venus of water. Once hydrogen escaped, there was no way to replace it. Water, once lost to space, does not return easily. The planet crossed another irreversible threshold. From that point forward, Venus was locked into its fate. Carbon dioxide continued to build up, reaching pressures dozens of times higher than Earth's atmosphere. The thick CO2 blanket trapped heat with relentless efficiency. Surface temperatures climbed to levels that sterilized the planet completely. Volcanic activity may have continued, releasing more gases and resurfacing large areas of the planet, but the climate state remained extreme. This is what makes the runaway greenhouse effect so unsettling. It is not merely an increase in temperature, it is a structural transformation of a planet's climate system. Once certain feedbacks dominate, returning to a previous state becomes extraordinarily difficult, if not impossible. Venus did not become hot because it wanted to. It became hot because physics allowed it, and because there was nothing left to counteract the process once it accelerated. Mars avoided this fate not because it was safer, but because it was smaller and colder. Its gravity was weaker. It lost much of its atmosphere early. Without a thick atmosphere, Mars could not trap heat effectively. Instead of overheating, it cooled. Instead of boiling its water, it froze it or lost it to space. Mars crossed a different threshold. Earth, meanwhile, sits in a narrow middle zone, warm enough to sustain liquid water, cool enough to prevent runaway evaporation, protected by magnetic fields, plate tectonics, and active cycles that redistribute carbon. The difference between these outcomes is not dramatic at first glance. A little more sunlight, a little less gravity, a slightly different early atmosphere. But over billions of years, these differences compound. This is why Venus is so important to climate science. It provides a real example of a planet that crossed the runaway greenhouse threshold, not in theory, not in models alone, in reality. Studying Venus helps scientists understand where that threshold lies and what factors influence it. This knowledge has become especially relevant as scientists study exoplanets. Many planets discovered around other stars orbit close to their suns. Many are Earth-sized or slightly larger. Many likely experience intense greenhouse effects. Venus-like worlds may be common. Earth-like worlds may be rare. This does not mean Earth is destined to become Venus. The differences between the two planets are significant, and Earth's climate system includes stabilizing mechanisms Venus lacks. But Venus serves as a reminder that planetary climates are not guaranteed to remain gentle indefinitely. They respond to physics, not intentions. From an exploration standpoint, the runaway greenhouse effect explains why Venus is not simply hot, but persistently hostile. This is not a temporary state. It is not a phase that will pass in a few million years. Venus has been in this condition for a very long time, and it will remain so for a very long time to come. Cooling Venus would require removing vast quantities of carbon dioxide from its atmosphere, or blocking incoming solar radiation on a planetary scale. These ideas exist as thought experiments, but they are far beyond anything humanity can realistically attempt. Mars, again, occupies a different category. Its problems are severe, but they are not self-reinforcing in the same way. Adding atmosphere to Mars, warming it, thickening it slightly, All of these are hypothetical but at least directionally consistent with making the planet more Earth-like rather than less. On Venus, intervention would need to fight the entire climate system at once. There is also an important psychological dimension to the Runaway greenhouse story. Humans are comfortable with gradual change. We adapt to seasons. We adapt to slow trends. What we struggle with are tipping points, moments when systems stop responding proportionally and begin responding exponentially. Venus embodies that fear. It represents a world that passed a point of no return without any single dramatic event marking the transition. No asteroid impact was required, no catastrophic explosion, just sunlight, water, gas, and time. This makes Venus unsettling in a way Mars is not. Mars feels like a world that faded. Venus feels like a world that overheated itself into permanence. When we talk about going to Mars instead of Venus, we're not just choosing between two planets. We're choosing between two types of planetary futures. One shaped by loss and thinning, the other shaped by excess and entrapment. Loss can sometimes be reversed. Excess is harder to undo. This distinction shapes exploration strategies in subtle ways. Engineers prefer environments where systems can be adjusted incrementally. Scientists prefer worlds where change happens slowly enough to observe and respond to. Mars offers both, even if in a harsh form. Venus does not. The Runaway greenhouse effect also reframes how we think about proximity. Venus is closer in space, but much farther in terms of intervention distance. Every solution must overcome a tightly coupled climate system that resists change. Mars, by comparison, is fragile. Its atmosphere is thin, its surface is cold, but fragility can be worked with. You can add energy, you can add pressure, you can build shelters and create pockets of stability. On Venus, stability is the problem. It is already stable in its extreme state. That stability makes Venus predictable, but not accessible. There is a quiet irony here. Venus's climate is incredibly stable. It does not swing wildly. It does not fluctuate dramatically between extremes. It is consistently hot, consistently dense, consistently hostile. From a systems perspective, it has achieved equilibrium. It is just not an equilibrium that allows life or exploration as we understand it. Mars, unstable and thin, leaves room for imagination. As this realization settled into scientific thinking, Venus's role shifted. It became less of a destination and more of a reference point, a boundary case, a warning encoded in planetary form. This does not diminish its importance. If anything, it elevates it. Venus tells us what happens when certain feedbacks dominate unchecked. It provides a full-scale example that no computer model can replace, but it also clarifies why we make the choices we do. When humans plan to step beyond Earth, they gravitate toward worlds that can be nudged, not worlds that push back relentlessly. They choose environments where survival depends on careful engineering, not on rewriting planetary physics. The Runaway greenhouse effect explains why Venus resists those ambitions so thoroughly. It is not merely hot by accident. It is hot because its entire system reinforces that condition. Venus stands as a reminder that closeness does not equal safety, and similarity does not guarantee familiarity. Sometimes the most important lesson a planet can offer is not how to live there, but how not to end up there at all, as we keep looking outward, choosing paths that allow for learning, adaptation, and continuation, rather than confrontation with a system that has already decided what it will be. Mars does not announce itself the way Venus does. It does not blaze in the twilight or demand attention from people who are not looking for it. Most nights, it blends quietly into the background, a faint reddish point that only stands out if you already know where to look. And yet, despite this modest presence, Mars has become the planet we talk about as if it is waiting for us, the cold desert next door. That phrase captures something essential about how we think of Mars. It frames the planet not as a mystery wrapped in clouds, but as a landscape, a place, somewhere with ground you can stand on, even if you would need a great deal of help to survive there. Somewhere hostile, yes, but legible, understandable. Mars is cold in a way that feels familiar, dry, thin, empty. Its average surface temperature sits around -60 degrees Celsius, but that number hides variation. Near the equator on a sunny day, temperatures can climb above freezing for short periods. At night, they plunge. At the poles, they remain brutally low. The planet is not uniformly frozen, but it is consistently unforgiving. Still, cold is a problem humans recognize. On Earth, we have lived in frozen environments for tens of thousands of years. We have crossed ice sheets, survived winters, built shelters, burned fuel, layered clothing, and learned how to trap heat. Our technology reflects this long relationship with cold. Insulation, heaters, thermal control systems, all of these are well understood. Mars, in that sense, feels like an extension of a known challenge rather than an entirely new one. The atmosphere tells a similar story. Mars's atmosphere is thin, about 1% of Earth's sea level pressure. You could not breathe it. You could not walk outside without protection. Liquid water cannot persist on the surface for long because the pressure is too low. But thin air, unlike crushing air, can be replaced. Inside a habitat, pressure can be created. Oxygen can be supplied. Carbon dioxide can be filtered. On Venus, pressure must be resisted constantly. On Mars, it must be added. That distinction matters more than it seems. Mars also offers ground that behaves predictably. Its soil, known as regolith, is dusty, rocky, and chemically reactive, but it is solid. It holds shape. It can be dug into. It can support structures. You can anchor equipment. You can imagine building on it, even if the reality remains far off. Venus's surface, though solid, is functionally inaccessible. The environment overwhelms any attempt to interact with it directly for long. Mars invites interaction. This is why rovers have thrived there. They drive, they climb, they drill, they analyze rocks layer by layer, slowly building a picture of the planet's history. Years pass, seasons change, dust settles. Mars allows time. Time is the key resource in exploration. Mars gives it grudgingly, but it gives it. The cold desert also carries signs of a past that feels eerily familiar. Orbital imagery has revealed dried river channels winding across ancient terrain. Delta structures fan out where water once flowed into basins. Minerals that form only in the presence of water are scattered across the surface. Polar ice caps grow and shrink with the seasons, composed of both water ice and frozen carbon dioxide. These features suggest that Mars was not always the world we see today. It was once warmer, wetter, capable of sustaining liquid water on its surface for extended periods. That history matters because it suggests continuity rather than rupture. Mars did not cross a sudden tipping point that locked it into an extreme state the way Venus did. Instead, it appears to have cooled gradually, losing its atmosphere over time as its magnetic field weakened and solar wind stripped away lighter gases. The planet faded. This gradual decline leaves traces that scientists can read. Layered sediments, chemical signatures, isotopic ratios. Mars's surface is a record, not a blank slate. It preserves its past rather than erasing it under pressure and heat. Venus, by contrast, has been resurfaced repeatedly by volcanic activity, its ancient features buried or melted beyond recognition. Mars holds on to memory. That makes it valuable not just as a destination, but as an archive. From a practical standpoint, Mars offers resources that are difficult to ignore. Water ice exists both at the poles and beneath the surface at lower latitudes. This water can be used for drinking, growing food, producing oxygen, and creating rocket fuel by splitting it into hydrogen and oxygen. Carbon dioxide, abundant in the atmosphere, can be processed into oxygen and fuel as well. These possibilities do not make Mars easy. They make it plausible. Plausibility is the currency of long-term planning. Mars's gravity, though weaker than Earth's, is still present. At about 38% of Earth's gravity, it allows for movement that feels grounded rather than floating. Astronauts could walk, carry equipment, perform tasks without the constant disorientation of microgravity. The long-term health effects of reduced gravity remain a concern, but they are not an unknown. On Venus, gravity is similar to Earth's, but the only survivable region is high in the atmosphere, where living conditions would be artificial and detached from any natural surface. Mars allows gravity and ground to work together. There is also the matter of light. Mars receives less sunlight than Earth, but not drastically less. Solar panels can function effectively, especially near the equator. Days on Mars, called sols, are only slightly longer than Earth days. This familiar rhythm matters more than it seems. Human biology responds to cycles. Sleep, work, and psychological stability are tied to regular patterns of light and dark. Venus's day is radically different. It rotates extremely slowly. A single day on Venus lasts longer than its year. The sun rises and sets at a pace that bears no resemblance to anything humans evolved under. For floating habitats, artificial lighting would be mandatory, disconnecting inhabitants entirely from the planet's natural rhythm. Mars again feels closer to home. The cold desert also feels honest. There is no disguise, no veil. What you see is what you get. Rusted plains, cratered highlands, thin skies. When missions fail on Mars, they fail in ways that are comprehensible. A landing goes wrong. A wheel breaks. A dust storm reduces power. These are engineering challenges, not existential ones. Venus failures feel inevitable. Mars failures feel fixable. This perception feeds into long-term ambition. You can iterate on Mars. You can learn from mistakes and apply those lessons to the next mission. Each rover builds on the last. Each lander improves. Progress accumulates. On Venus, each mission starts almost from scratch, constrained by the same brutal limits. Mars also occupies a unique place in human imagination because it sits at the edge of habitability without falling completely outside it. It is not alive, but it looks like it once could have been. It is not welcoming, but it is not utterly alien. That balance makes it compelling. Venus feels like a world that closed itself off. Mars feels like a world that fell asleep. There is also a strategic element to Mars's position. It is far enough from Earth to require serious commitment, but close enough that communication delays remain manageable. Signals take minutes, not hours. Emergency planning, while still difficult, remains within human timescales. Return missions are possible. Rescue scenarios, while extreme, are not entirely implausible. Mars becomes a stepping stone rather than an endpoint. This matters when thinking about exploration beyond Mars. Techniques developed there can be adapted for asteroids, moons, and eventually more distant destinations. Mars serves as a proving ground. Venus does not offer the same training environment, and yet Mars is not forgiving. Radiation exposure remains a serious concern. Without a strong magnetic field or thick atmosphere, the surface is bombarded by cosmic rays and solar particles. Long-term human habitation would require shielding, whether through buried habitats, thick walls, or natural features like lava tubes. Dust storms can envelop the entire planet, blocking sunlight for weeks. Fine dust infiltrates machinery, clings to surfaces, and complicates maintenance. The soil contains perchlorates, toxic compounds that must be handled carefully. Mars demands respect, but it does not reject effort outright. This distinction underlies almost every plan drawn up for human exploration. Mars is difficult, but difficulty can be met with preparation. Venus is absolute. It sets limits that technology cannot currently negotiate. The cold desert next door also provides emotional space. It allows humans to project futures, not utopian futures, but working ones, habitats, research stations, small communities focused on science and survival. The imagery is grounded, dusty boots, pressurized modules, rovers parked outside like trucks in a frozen outpost. Venus does not lend itself to that imagery. Floating cities sound elegant, but they remain abstract. They lack the tactile quality that makes Mars feel achievable. This is not a failure of imagination, it is a reflection of constraints. Mars has constraints we can push against. Venus has constraints that push back harder. Thin air versus crushing skies, loss versus excess. These are not just descriptive differences, they are strategic ones. Mars may not shine brightly in the sky, but it offers something Venus does not. It offers the possibility of staying long enough to learn, to adapt, and to leave behind more than footprints before moving on. At first it sounds backwards. Cold feels dangerous. Cold kills quickly. Cold freezes water, stiffens muscles, drains batteries, and turns simple mistakes into emergencies. Heat, on the other hand, feels familiar, comfortable, inviting. We seek it out. We sit in sunlight. We warm our hands by fires. We associate heat with life. And yet, when engineers, scientists, and mission planners look at other planets, they come to a conclusion that feels counterintuitive, but is remarkably consistent. Cold is easier than hot. Not emotionally, not instinctively, but physically, mechanically, and structurally. When it comes to keeping humans and machines alive in hostile environments, cold offers options. Heat removes them. The difference begins with energy flow. Cold, at its core, is an absence of heat. Hot is an excess of it. This distinction matters because adding energy is usually easier than removing it, especially when the surrounding environment is already saturated with heat. If you are cold, you can add insulation, generate warmth, concentrate energy. If you are hot, you must find a way to move heat away, and that becomes dramatically harder when there is nowhere for it to go. On Mars, the environment is cold because energy escapes easily. The atmosphere is thin, heat radiates into space, temperature drops quickly after sunset. For humans and machines, this means the primary task is retention. Keep heat in, prevent loss, slow the flow of energy outward. This is a problem we understand. On Earth, we solve it every day. Buildings are insulated, clothing traps air, electronics are designed to operate within controlled temperature ranges. Spacecraft already deal with extreme cold in orbit, using heaters, reflective coatings, and thermal blankets to maintain stability. Mars extends this challenge, but it does not redefine it. Venus does. On Venus, the problem is not keeping heat, it is escaping it. The environment is already hotter than most systems are designed to tolerate. The atmosphere is thick, dense, and efficient at transferring heat back into anything placed within it. There is no cold sink. There is no effective radiative escape path. Heat wants to go from hot to cold. On Venus, everything is hot. Imagine trying to cool a computer by placing it inside an oven. No matter how clever your cooling system is, it will struggle because the surrounding air keeps forcing heat back in. Fans do nothing if the air they move is already hotter than the object they are trying to cool. Radiators become useless if there is no temperature gradient to exploit. This is why Venus landers fail so quickly. Their electronics generate heat as they operate. On Mars, that waste heat can actually be helpful, keeping systems warm. On Venus, waste heat becomes an additional burden layered on top of an already extreme environment. Cooling systems must fight both internal and external heat simultaneously. Pressure makes this worse. High pressure increases the rate at which heat is transferred. The dense Venusian atmosphere conducts heat efficiently. Any object placed on the surface is rapidly brought into thermal equilibrium with its surroundings. Insulation helps, but only temporarily. Over time, heat seeps in. On Mars, low pressure slows heat transfer. The thin air is a poor conductor. Insulation works extremely well. Heat leaks out slowly, giving systems time to respond and adjust. This is one of the reasons Mars rovers can survive nights that plunge far below freezing. They are insulated, they carry heaters, they are designed to ride out cold periods and warm up again with the rising sun. On Venus, there is no warm-up cycle. There is no night that cools things down. There is no pause. Cold also offers structural advantages. Materials behave more predictably at low temperatures than at high ones. Metals become brittle when extremely cold, but this can be accounted for in design. Polymers stiffen, lubricants thicken, batteries lose efficiency, but none of these effects are sudden or catastrophic if properly managed. High temperatures, especially sustained high temperatures, cause materials to creep, deform, oxidize, and fail in ways that are difficult to reverse. Seals degrade. Electronics suffer thermal runaway. Components that rely on precise tolerances drift out of specification. On Venus, these processes are relentless. There is no recovery period. Even the strongest alloys eventually weaken. Even the best insulation eventually saturates. Mars allows maintenance windows. Venus does not. There is also the question of human physiology. The human body generates heat constantly. At rest, at work, even while sleeping, metabolism produces warmth. On Earth, this heat dissipates naturally into the surrounding air. In cold environments, the challenge is preventing too much heat loss. In hot environments, the challenge is preventing heat buildup. Humans are remarkably good at dealing with cold. Clothing, shelter, and fire have extended our range across the planet. We have lived in Arctic regions for thousands of years. We understand how to trap heat and regulate exposure. Heat tolerance, however, has limits. At high temperatures, the body struggles to shed excess heat. Sweating becomes ineffective when the surrounding air is hot or humid. Core temperature rises, enzymes fail, organs shut down. This happens even on Earth, at temperatures far below those found on Venus. On Venus, the surface temperature is so high that the human body would overheat instantly. There is no physiological adaptation that could cope with it. Even advanced cooling suits would fail without an external heat sink. Mars, by contrast, is lethally cold, but cold can be mitigated with insulation and active heating. The body's own heat production becomes an asset rather than a liability. This is why spacesuits are designed primarily to manage cold rather than heat. Astronauts in space face extreme temperature swings, but overheating is often a bigger concern than freezing, even in orbit. On Mars, the balance shifts toward cold, but within a range that engineering can handle. On Venus, there is no balance. Energy generation also favors cold environments. On Mars, solar panels work reasonably well. The sunlight is weaker than on Earth, but still sufficient. Nuclear power sources perform reliably in cold conditions. Waste heat from power generation can be reused to warm habitats and equipment. On Venus, solar energy is abundant above the clouds, but nearly useless at the surface. The thick atmosphere blocks and scatters sunlight. Any power system must operate in extreme heat, compounding cooling challenges. Nuclear systems face the same problem. They generate heat in an environment already saturated with it. Cold environments give you flexibility. Hot environments remove it. There is a deeper systems-level reason why cold is easier than hot, and it has to do with control. Cold environments tend to be unstable in the sense that energy flows out. This instability allows intervention. You can slow the loss. You can add energy. You can create pockets of warmth. You can build barriers. Hot environments that are stable, like Venus, resist change. The system wants to stay hot. Any attempt to cool a small region must constantly fight the surrounding conditions. The environment pushes back. Mars's cold is a kind of openness. Venus's heat is a kind of closure. This distinction shapes not only hardware design but mission philosophy. Mars missions are designed for longevity. Rovers are expected to last years. Habitats are envisioned to operate for decades. Problems will occur, but they can be addressed incrementally. Venus missions are designed for speed, gather data quickly, Accept failure. Do not expect repair. Do not expect extension. Time, again, is the deciding factor. Cold buys time. Heat consumes it. There is also the issue of storage and preservation. On Mars, cold helps preserve materials. Organic compounds degrade more slowly. Radiation remains a concern, but chemical reactions are slowed by low temperatures. Samples can remain stable. On Venus, high temperatures accelerate everything. Chemical reactions proceed rapidly. Materials break down. Data storage becomes unreliable. Even simple mechanical parts suffer accelerated wear. This is why Mars is such a rich archive of planetary history. Its cold, dry environment preserves ancient features. Venus's heat and pressure erase them. From an exploration standpoint, cold means you can leave something behind and come back to it. Heat means you cannot. This logic extends to future planning. If humans are to establish a presence beyond Earth, they need environments where systems can fail gracefully rather than catastrophically. A heater failure in a cold environment is dangerous, but it is often detectable and correctable. A cooling failure in a hot environment can be immediate and final. Mars offers margins. Venus removes them. This is not to say that Mars is safe. It is not. Cold can kill quickly if systems fail. Radiation exposure remains a serious challenge. Dust storms can cripple power generation. Isolation takes a psychological toll. But all of these dangers exist within a framework that allows response. Venus's dangers collapse response time to almost nothing. Even proposed solutions for Venus reflect this imbalance. Floating habitats in the upper atmosphere are often cited as a way to avoid surface heat. At those altitudes, temperature and pressure are closer to Earth-like. But even there, the environment remains chemically hostile, dynamically unstable, and disconnected from the surface. Any failure sends a habitat downward into conditions from which recovery is impossible. Mars habitats, by contrast, fail onto ground that, while dangerous, is not instantly destructive. Cold, in this sense, is forgiving. Not kind, but forgiving. This forgiveness extends to learning. Mars allows iteration. You can send multiple missions, refine designs, improve systems, and gradually build experience. Each success and failure informs the next attempt. Venus allows far less iteration. Each mission faces the same hard limits. Progress accumulates slowly because operating time is short. This difference shapes funding, ambition, and public support. Long-term projects require visible progress. Mars delivers that. Venus, constrained by physics, does not in the same way. It is also worth noting that cold environments dominate much of the universe. Space itself is cold. Planets far from their stars are cold. Even many exoplanets of interest exist in temperature regimes closer to Mars than to Venus. Learning how to operate in cold, thin atmospheres prepares us for a broader range of destinations. Learning how to survive Venus prepares us for Venus. That specificity matters. So when mission planners say cold is easier than hot, they are not dismissing the dangers of cold. They are acknowledging a hierarchy of difficulty rooted in thermodynamics, material science, physiology, and systems engineering. Cold gives you room to maneuver. Heat boxes you in. Mars, as the cold desert next door, sits on the manageable side of that divide. It challenges us, but it does not nullify our tools outright. Venus, with its runaway greenhouse and crushing skies, represents the opposite extreme, where even the best tools struggle to function at all. This is why the closer planet is not the chosen one. Not because distance does not matter, but because temperature, pressure, and energy flow matter more. Cold, in the end, is a problem you can work on. Heat, when it reaches Venus's level, is a verdict. And that verdict quietly shapes every decision about where humans might someday live, work, and look up at a sky that challenges them without crushing them under its weight. The word itself carries a lot of weight. Colonization. It sounds bold, decisive, almost cinematic, It conjures images of domes rising from red soil, people working methodically under alien skies, a future that feels earned through effort rather than imagined through hope alone. But when scientists and engineers use the word in serious contexts, they mean something far quieter and far more constrained. They mean sustained presence. They mean the ability to live somewhere without constant resupply from Earth, to survive setbacks, to fix what breaks, to grow food, to recycle air and water, to endure not just for weeks or months but for years. Colonization, in this practical sense, is not about conquest or ownership. It is about stability. And when framed this way, the dream narrows very quickly. Mars sits at the edge of that narrowing. Not because it is friendly, but because it allows the idea to exist without immediately collapsing under the weight of physics. It offers just enough compatibility, just enough margin, that serious people can outline scenarios without having to invent entirely new laws of nature to support them. This is where the conversation shifts from curiosity to logistics. To sustain a human presence, you need air, water, food, energy, and shelter. You need redundancy. You need repairability. You need time to respond when systems fail. Mars does not provide these things freely, but it allows them to be created. Start with air. Mars's atmosphere is thin and unbreathable, but it is rich in carbon dioxide. That is not a drawback, it is a resource. Carbon dioxide can be processed to extract oxygen. This is not theoretical, it has already been demonstrated. The MOXIE experiment aboard the Perseverance rover successfully produced oxygen from the Martian atmosphere, proving that in situ resource utilization is possible. This matters because air is heavy. Launching oxygen from Earth is expensive. Producing it locally changes the equation entirely. It turns Mars from a place that must be supplied into a place that can support itself, at least partially. Venus also has an atmosphere rich in carbon dioxide, but the similarity ends there. On Venus, the atmosphere is so dense and so hot that processing it becomes an extreme challenge. Equipment would need to operate in conditions that quickly destroy conventional machinery. On Mars, processing can happen inside protected habitats, at manageable temperatures and pressures. Then there is water. Water is the cornerstone of any long-term human presence. It is needed for drinking, hygiene, agriculture, oxygen production, and fuel. Mars has water, not in rivers or lakes but locked in ice, beneath the surface, at the poles, embedded in regolith. This ice is accessible. It can be mined, melted, purified, recycled. Again, this is not science fiction. Radar data has mapped subsurface ice deposits. Landers have confirmed its presence. The challenge is scale, not existence. Venus, by contrast, has almost no water. What little remains is locked high in the atmosphere as trace vapor. Extracting usable quantities would be extraordinarily inefficient. The planet lost its water long ago, and it shows no signs of replenishment. Food follows water. On Mars, controlled agriculture is difficult but plausible. Plants do not need open air. They need light, water, nutrients, and protection. Hydroponic systems can function in sealed environments. Martian regolith, though toxic in its raw form due to perchlorates, can potentially be processed into usable growing media. This is an engineering challenge, not a physical impossibility. On Venus, agriculture would need to exist entirely within sealed, floating structures, disconnected from any natural resource base. Soil would need to be imported or manufactured. Water would need to be recycled with near-perfect efficiency. Any failure would cascade quickly. Mars allows experimentation. Venus demands perfection. Energy is another dividing line. Mars receives less sunlight than Earth, but enough to power solar systems, especially when combined with energy storage. Nuclear reactors are also viable. Waste heat can be repurposed to warm habitats, melt ice, and maintain system stability. On Venus, solar energy is abundant above the clouds, but nearly inaccessible at the surface. Floating habitats could use solar power, but they would still face extreme atmospheric dynamics, corrosion, and the ever-present risk of descent into lethal conditions. Energy on Mars is hard but predictable. Energy on Venus is abundant but precarious. Shelter ties all of this together. On Mars, shelters can be built on the surface or underground. Regolith can be piled over habitats to provide radiation shielding. Lava tubes, vast underground caverns formed by ancient volcanic activity, offer natural protection. These structures are stable, solid, and widespread. Living underground may sound claustrophobic, but it is a known solution. Humans already live and work underground on Earth. Mining operations, research facilities, and shelters have proven that extended subterranean living is possible. On Venus, shelter is not a matter of location, it is a matter of suspension. Habitats must float, maintaining buoyancy at all times. Structural integrity is constantly threatened by corrosion, turbulence, and material fatigue. There is no stable surface environment to retreat to. The ground on Mars may be cold and dusty, but it exists. The ground on Venus might as well not. This brings us to repair. No system lasts forever. Components wear out. Seals degrade. Electronics fail. On Earth, repair is possible because materials behave within known limits. On Mars, despite the cold and radiation, materials degrade slowly enough to allow maintenance. Tools work. Hands function. Replacement parts can be fabricated, potentially even printed on site. On Venus, repair is constrained by time. You do not fix things leisurely in an environment that actively destroys your tools while you work. Even in floating habitats, exposure to the atmosphere introduces constant stress. Maintenance becomes a race rather than a routine. Time, once again, becomes the deciding factor. Colonization is not about surviving the environment at its best. It is about surviving it at its worst. It is about enduring dust storms, power outages, equipment failures, illness, and human error. It is about margin. Mars offers margin. Venus offers almost none. There is also the question of psychology. Long-term habitation requires not just physical survival, but mental resilience. People need routines, variation, a sense of progress. They need to feel that effort accumulates rather than resets. Mars provides landmarks, horizons, terrain, a sense of movement. Even inside a habitat, the knowledge that there is ground outside, that you can go somewhere, even briefly, matters deeply. Venus's floating environments would be visually monotonous and psychologically isolating. There would be no walks, no exploration in the usual sense, no gradual expansion of territory. Every habitat would be an island suspended over a lethal descent. Humans can adapt to extreme conditions, but adaptation has limits. Mars feels like a place you could get better at living in over time. Venus feels like a place you would always be barely tolerating. This distinction shapes how colonization is discussed seriously, rather than aspirationally. Mars is framed as a frontier. Venus is framed as an experiment. Even the concept of terraforming reflects this divide. Terraforming Mars, while still far beyond our current capabilities, is at least directionally aligned with making the planet more Earth-like, thickening the atmosphere, warming the surface, introducing water vapor. These ideas, however speculative, push Mars toward habitability rather than away from it. Terraforming Venus would require the opposite, cooling the planet, removing or sequestering vast amounts of carbon dioxide, blocking sunlight. These are interventions on a scale that borders on fantasy. They would need to undo a planetary system that has been stable for billions of years. One direction works with the planet's trajectory, the other fights it. Colonization, in practice, always follows the path of least resistance, not because humans lack ambition, but because ambition must survive contact with reality. Mars resists us gently, steadily, in ways that allow learning. Venus resists absolutely. There is also the matter of expansion. A colony that cannot grow is not a colony. It is an outpost. Mars offers room. Not in the sense of abundance, but in the sense of scalability. More habitats can be added. More sites can be explored. Infrastructure can spread. Venus's viable zone is narrow and constrained. Expansion would be limited to additional floating platforms, each carrying the same risks and dependencies. Mars allows geography to matter. Venus does not. This does not mean that Venus has no role in humanity's future. It does. Studying its atmosphere, understanding its chemistry, learning how to operate in extreme environments, all of this has value. But value is not the same as viability. The practical dream of colonization is not about choosing the most interesting planet. It is about choosing the one that allows mistakes, repairs, and gradual improvement. Mars allows us to imagine failure without finality. Venus does not. That difference shapes everything from funding priorities to engineering curricula. It influences which technologies are developed, which missions are approved, and which futures feel concrete enough to pursue. When people talk about building a future on Mars, they are not imagining comfort. They're imagining continuity, the ability to keep going, to adapt, to refine systems, to pass knowledge forward rather than start from scratch every time. Mars offers that possibility. It doesn't take long once people start talking seriously about living on Mars before the conversation stretches further. Not just habitats and domes, not just sealed greenhouses and buried modules, something bigger, something planetary. What if we didn't just adapt to Mars? What if we changed it? Terraforming is one of those ideas that sounds almost magical at first. The word itself feels grand. To terraform is to reshape a world until it resembles Earth. Thicker air, warmer temperatures, flowing water, blue skies. It suggests control on a scale that borders on myth. And yet when scientists discuss it, the tone is usually far more restrained. Terraforming is not a weekend project. It is not even a century project. It is a concept that lives on the edge between physics, engineering, and imagination. Still, if there is any nearby planet where the idea can be discussed without immediately collapsing into absurdity, it is Mars, not Venus. That distinction is important. Start with what Mars lacks. Its atmosphere is thin. Its surface pressure is too low for stable liquid water. Its temperatures are too cold for comfortable human activity. Radiation levels are high because there is no thick atmosphere or strong magnetic field to provide shielding. Now consider what Mars has. Carbon dioxide is present in the atmosphere and frozen in the polar ice caps. Water ice exists underground. The planet's gravity, while weaker than Earth's, is not negligible. The day length is almost identical to Earth's. Solar energy, though reduced, is available. These are not small details, they are footholds. Many terraforming proposals for Mars begin with thickening the atmosphere. If you could release more carbon dioxide into the air, perhaps by heating the polar caps or triggering industrial-scale chemical reactions, the greenhouse effect could intensify. A thicker atmosphere would trap more heat. Higher temperatures would melt more ice. Liquid water might begin to flow, at least seasonally. This idea has been explored in scientific literature for decades. The mechanisms are debated, the feasibility uncertain, but the direction is clear. Mars could, in principle, be nudged toward a warmer, denser state. But there are limits. Recent studies suggest that Mars may not contain enough accessible carbon dioxide to create a fully Earth-like atmosphere. Even if all the CO2 locked in the ice caps and regolith were released, the resulting pressure might still fall short of what humans require without pressure suits. Terraforming Mars, if it is possible at all, would likely produce something intermediate. Not Earth 2.0, but a thicker, warmer Mars. A world where humans might walk outside with lighter protection. A world where liquid water is stable in some regions. A world that feels less extreme. That is the fantasy. But even this moderated version of terraforming faces immense challenges. Releasing gases requires energy. Industrial-scale operations on another planet would demand infrastructure that does not yet exist, and even if warming began, maintaining it would require ongoing input. Mars lacks a strong magnetic field, which means solar wind would continue stripping away atmospheric gases over time. Terraforming is not a one-time switch, it is a continuous commitment. And yet, despite these obstacles, the idea persists for Mars because it does not violate planetary physics outright. It works with existing processes rather than against them. Now compare that to Venus. If Mars is too cold and too thin, Venus is too hot and too thick. Its atmosphere is overwhelmingly carbon dioxide. Its surface temperature is far beyond comfortable. Its pressure is crushing. Its runaway greenhouse effect is stable and self-reinforcing. Terraforming Venus would require the opposite of Mars. Instead of adding heat and gas, you would need to remove it. Vast quantities of carbon dioxide would need to be sequestered or chemically altered. Sunlight would need to be blocked or reflected before it reached the surface. The entire climate system would need to be shifted out of equilibrium. Some proposals suggest deploying massive solar shades in orbit to reduce incoming energy. Others imagine chemically converting carbon dioxide into solid carbonates. Still others envision introducing engineered organisms to transform the atmosphere over centuries. Each of these ideas runs into the same problem: scale. The scale of intervention required to cool Venus is staggering. The planet has been in its current state for billions of years. Its atmosphere contains orders of magnitude more carbon dioxide than Earth's. Its surface is hot not by accident, but by systemic design. Even if you could block sunlight, the thick atmosphere would retain heat for an extremely long time. Cooling would take centuries or millennia. Removing carbon dioxide would require chemical processes operating at planetary scale. Mars, by contrast, requires enhancement, not reversal. There is also the matter of starting conditions. On Mars, any thickening of the atmosphere moves conditions toward habitability. On Venus, any miscalculation could worsen instability. Attempts to intervene could create unpredictable feedbacks. Terraforming fantasies often gloss over this difference because the word itself is intoxicating. It suggests mastery. It implies that planets are clay waiting for sculptors. But planets are systems. They respond to forces according to laws that do not bend easily. Mars's system is underpowered. Venus's is overpowered. It is far easier to amplify a weak greenhouse effect than to dismantle a runaway one. There is also a temporal dimension. Terraforming Mars, if it ever happens, would take centuries at minimum, more likely thousands of years. This is not a project for a single generation. It is a long arc of incremental change. Terraforming Venus would likely take far longer, assuming it could be done at all. It would require global coordination, massive infrastructure, and technological capabilities that humanity does not yet possess. In practical terms, this pushes Venus's terraforming into the realm of far future speculation, while Mars's remains in the realm of distant but conceivable engineering. This is why Mars dominates the conversation. Even then, many scientists remain skeptical of terraforming in any form. They argue that focusing on local habitats and contained environments is far more realistic than attempting planetary transformation. Building controlled ecosystems inside sealed structures is orders of magnitude simpler than rewriting an entire atmosphere, and they are probably right. Terraforming fantasies often reveal more about human psychology than about planetary science. They reflect a desire not just to survive elsewhere, but to feel at home, to see blue skies instead of dusty red or yellow haze, to walk without helmets, to breathe without machines. But there is a difference between making a place livable and making it comfortable. Mars can potentially be made livable in contained ways. Venus cannot, at least not without leaps in technology that border on science fiction. Even floating habitats on Venus, often presented as an elegant compromise, are not terraforming in the traditional sense. They are adaptation strategies. They leave the planet itself unchanged, carving out small bubbles of survivability within an otherwise hostile system. Mars allows both adaptation and potentially transformation. Venus allows only adaptation, and even that is limited. This asymmetry explains why terraforming discussions cluster around Mars. It is not because Mars is easy. It is because Mars offers gradients rather than walls. You can imagine warming it by a few degrees. You can imagine increasing pressure incrementally. You can imagine expanding habitable zones slowly over time. Venus offers almost no incremental pathway. It is an all-or-nothing challenge, and all-or-nothing projects rarely begin. There is also an ethical dimension to terraforming that deserves attention. If Mars ever hosted microbial life, altering its environment could erase that history. Some argue that preserving other worlds in their natural state is more important than reshaping them for human use. This debate is real and ongoing. On Venus, the ethical dilemma is less immediate because the surface is almost certainly sterile. But in the upper atmosphere, there have been discussions about the possibility of microbial life in temperate cloud layers. Terraforming could disrupt unknown ecosystems there as well. Even fantasies carry consequences. Ultimately, terraforming fantasies highlight the deeper reason why Mars draws our attention more than Venus. Mars feels unfinished, Venus feels settled. An unfinished world invites intervention. A settled one resists it. Mars's cold desert can be imagined as a canvas, even if that metaphor oversimplifies reality. Venus's furnace feels like a completed equation. Once the idea of terraforming enters the conversation, Venus inevitably follows, not because it seems practical, but because it feels unfinished in a different way. Mars feels empty. Venus feels excessive, and excess invites the question of reversal. Could it ever be saved? The word saved already carries assumptions. It implies that Venus is broken in a way that can be repaired, that its current state is a deviation rather than an outcome. From a human perspective, that makes sense. Venus is hostile to us, therefore it feels wrong. But from a planetary perspective, Venus is not malfunctioning. It is stable. It is doing exactly what its physics allows and reinforces. That stability is the first obstacle. Any attempt to change Venus must overcome a system that strongly resists change. The planet's atmosphere, temperature, and pressure are not teetering on the edge of balance. They are locked in. Energy flows reinforce the greenhouse effect rather than weakening it. Carbon dioxide dominates not temporarily but structurally. Saving Venus would not mean nudging a process. It would mean dismantling one. Most proposed ideas begin with the same basic recognition. Venus is hot because it receives too much usable solar energy and traps it too efficiently. So the first step, in theory, would be to reduce the energy input. One often cited idea involves placing a massive solar shade or mirror in space, positioned between Venus and the Sun. This structure would block or reflect a significant portion of incoming sunlight, reducing the energy reaching the atmosphere. Over time, the planet would begin to cool. In principle, this makes sense. Reduce the input, and the system responds. In practice, the scale is overwhelming. The shade would need to be enormous, comparable in size to the planet itself. It would need to remain precisely positioned for centuries or millennia. It would need to withstand constant exposure to solar radiation and micrometeoroids. Any failure or drift would reintroduce heat. Even if such a structure could be built and maintained, cooling Venus would not be quick. The atmosphere stores vast amounts of thermal energy. Blocking sunlight would slow further heating, but the planet would retain heat for a very long time. Cooling would occur on geological timescales, not human ones, and cooling alone would not solve the pressure problem. Venus's atmosphere contains an immense quantity of carbon dioxide. Even if temperatures dropped significantly, the pressure would remain crushing unless the gas itself were removed or transformed. This leads to the next category of proposals. What if the carbon dioxide could be sequestered? Some ideas imagine chemically binding CO2 into solid carbonates by reacting it with surface minerals. On Earth, this happens naturally through weathering and plate tectonics. On Venus, the surface is hot, dry, and lacks liquid water, making such reactions inefficient. Others suggest introducing engineered organisms capable of converting carbon dioxide into other compounds. This idea borrows from biology, but it runs into immediate problems. No known organism can survive Venus's surface conditions. Even in the upper atmosphere, conditions are harsh, acidic, and dynamically unstable. Biology, at least as we understand it, has nowhere to start. More speculative concepts imagine removing the atmosphere entirely, perhaps by stripping it away mechanically or ejecting it into space using massive energy inputs. This idea is sometimes mentioned casually, but when examined closely, it becomes clear how impractical it is. The amount of energy required to remove Venus's atmosphere exceeds anything humanity could generate for the foreseeable future. It is not a matter of clever engineering, it is a matter of scale that borders on the absurd. Another approach focuses on transformation rather than removal. What if carbon dioxide could be split into carbon and oxygen using high-energy processes? In theory, this could reduce atmospheric pressure and create breathable oxygen. In practice, splitting CO2 on a planetary scale would require energy comparable to that released by stellar processes. The oxygen produced would also need to be managed carefully. Oxygen at high concentrations is reactive and dangerous. The carbon would need to be stored or stabilized somehow. Each solution generates new problems. This is a recurring theme with Venus. Every intervention creates cascading consequences that demand further intervention. The system is tightly coupled. You cannot change one variable without affecting many others. Mars, by comparison, has loosely coupled systems. You can add atmosphere without immediately triggering catastrophic feedback. You can warm the surface incrementally. You can test, observe, adjust. Venus does not offer that luxury. Even the often discussed idea of floating cities, while intriguing, does not actually save Venus. It avoids the surface rather than changing it. At altitudes around 50 kilometers above the ground, Venus's temperature and pressure are surprisingly Earth-like. This narrow band has inspired proposals for aerostat habitats, massive balloons or platforms that could float indefinitely. In this zone, humans could theoretically survive with appropriate protection against acid clouds and winds. Solar energy is abundant. Gravity is comfortable. The idea is elegant, but it is also fragile. Floating habitats would exist in a dynamic atmosphere, with powerful winds and chemical corrosion. Maintenance would be constant. Redundancy would be critical. Any major failure would result in descent into an environment that offers no recovery. More importantly, floating habitats do not scale easily. They remain isolated structures, disconnected from the planet's surface and from each other. They do not create a self-sustaining planetary ecosystem. They create outposts suspended over a world that remains unchanged. This is adaptation, not salvation. The deeper issue is that Venus's problems are not surface level. They are planetary. The runaway greenhouse effect is not something you can turn off locally. It operates globally, driven by the interaction between atmosphere, sunlight, and planetary chemistry. Saving Venus would require altering its entire climate system. That brings us to a hard truth that often goes unspoken. Venus may not need saving. From a cosmic perspective, Venus is not a failure. It is one of many possible stable planetary outcomes. It followed a path allowed by physics. Earth followed a different one. Mars followed another still. We call Venus hostile because it is hostile to us. But hostility is relative. Venus does not violate any natural law. It simply does not align with human requirements. This reframing changes the question. Instead of asking whether Venus can be saved, we might ask whether it should be changed at all, whether imposing our definition of habitability on another world is justified, especially when the cost is so extreme. There is also the question of timescale. Any meaningful transformation of Venus would take far longer than human civilizations have existed. It would span thousands or millions of years. The people who began such a project would never see its outcome. The motivations would need to be philosophical rather than practical. Mars again contrasts sharply here. Changes on Mars, even small ones, could have effects within centuries. Human lifetimes could overlap with measurable progress. That matters for commitment. Projects that never yield visible results struggle to survive politically, economically, and culturally. Venus's salvation, if it exists at all, is too distant to anchor ambition. There is also a risk in framing Venus as something that needs fixing. It shifts attention away from what Venus actually offers now, a natural laboratory for extreme climate, a warning encoded in planetary form, a counterexample that helps define the boundaries of habitability. Understanding Venus may be far more valuable than trying to change it. Many scientists argue that the most responsible approach is to study Venus as it is, not as we wish it were. To learn how runaway greenhouse effects begin, to identify tipping points, to refine climate models, to apply those lessons to Earth and to exoplanets. In this sense, Venus may already be doing its most important work. Mars invites us to build. Venus invites us to reflect. Saving Venus would require not only technological breakthroughs, but a shift in how humanity defines success in space. It would require valuing projects that extend beyond any conceivable payoff. It would require patience on a scale that civilizations rarely sustain. This does not make the idea meaningless. It makes it revealing. The fact that Venus resists salvation so thoroughly is itself informative. It tells us that some planetary paths are one way, that prevention matters more than cure, that thresholds exist which, once crossed, do not politely reverse. And this realization feeds back into why Mars remains the focus of our efforts. Mars is damaged, but not locked. Venus is locked. The difference between those two states is subtle in theory and decisive in practice. Once the discussion moves away from climate and habitability, away from clouds and deserts and into the realm of actually getting somewhere, the romance of planetary choice gives way to numbers, distances, velocities, energies. This is where intuition often fails, because space does not behave the way everyday travel does. Closer on a map does not mean cheaper. Brighter in the sky does not mean easier to reach, and the most direct-looking path is rarely the one rockets actually take. This is where orbital mechanics quietly takes over. From Earth, Venus does appear closer than Mars much of the time, but spacecraft do not travel in straight lines through space like airplanes crossing continents. They move along curved paths shaped by gravity, momentum, and timing. Every launch is a negotiation with physics, and physics is indifferent to what feels intuitive. To leave Earth at all, a spacecraft must first climb out of a deep gravity well. That alone requires enormous energy. Once free of Earth's pull, the spacecraft does not simply point at its destination and fire engines until it arrives. That would be wildly inefficient. Instead, it slips into an orbit around the Sun, one carefully chosen to intersect the orbit of another planet at precisely the right time. This is why launch windows matter. Mars missions are launched roughly every 26 months, when Earth and Mars align in a way that minimizes the energy required to transfer from one orbit to the other. Venus missions have their own windows, often more frequent, but the geometry is different. Going inward toward the Sun is not the same as going outward. To reach Mars, a spacecraft must gain energy relative to the Sun. Earth orbits at about 30 kilometers per second. Mars orbits more slowly, around 24 kilometers per second. To climb outward, the spacecraft increases its orbital energy, stretching its path into a larger ellipse that intersects Mars's orbit. To reach Venus, the spacecraft must do the opposite. It must lose orbital energy, falling inward toward the Sun. This may sound easier, but shedding energy is not trivial. Rockets are excellent at adding velocity. Removing it requires careful planning. Gravity assists, or extended engine burns. In practical terms, both journeys are demanding, but they stress systems differently. There is also the issue of arrival. Reaching a planet is only half the challenge. Slowing down enough to be captured by its gravity is the other half. On Mars, the thin atmosphere allows for a technique called aerobraking. A spacecraft can dip into the atmosphere repeatedly, using drag to slow down gradually without burning large amounts of fuel. This method has been used successfully many times. Venus's atmosphere is far thicker, which might seem helpful at first. More drag means easier slowing, right? In reality, the density and heat create severe constraints. Aerobraking at Venus must be done extremely carefully to avoid overheating or destabilizing the spacecraft. The margin for error is narrow. Landing amplifies this difference. Mars landings are notoriously difficult, often described as threading a needle at high speed. The atmosphere is thick enough to cause heating, but too thin to provide sufficient drag on its own. This forces complex landing sequences involving heat shields, parachutes, and powered descent. Venus landings face a different nightmare. The atmosphere is thick enough to slow a spacecraft dramatically, but the heat generated during entry is extreme. Parachutes must survive high temperatures and corrosive chemistry. Descent takes longer, which increases exposure to hostile conditions. By the time a lander reaches the surface, it has already endured tremendous stress. Mars landers emerge into cold. Venus landers emerge into an oven. Fuel planning reflects this contrast. Mars missions are often designed with the possibility of refueling using local resources. Water can be split into hydrogen and oxygen. Carbon dioxide can be processed into methane and oxygen. These ideas are being actively tested and refined. In situ fuel production is central to many human mission plans. On Venus, local fuel production is theoretically possible in the atmosphere, but the environment complicates every step. High temperatures accelerate unwanted reactions. Corrosive compounds degrade equipment. Maintaining precision chemical processes becomes extraordinarily difficult. Returning from Mars while challenging is considered achievable. Returning from Venus's surface is far more problematic. Launching a vehicle through that dense atmosphere requires immense thrust and robust materials capable of withstanding extreme heat and pressure. Orbital math also influences communication. Mars is far enough from Earth that signal delays range from a few minutes to over 20 minutes one way, depending on orbital positions. This makes real-time control impossible but manageable. Autonomous systems handle most operations, with humans planning ahead and responding with delays. Venus, being closer, offers shorter communication delays. But this advantage is offset by environmental limitations. Shorter delays are less useful when operational lifetimes are measured in hours rather than years. Time again becomes the deciding factor. Mission designers think in terms of return on investment. A Mars rover may operate for a decade. A Venus lander may operate for a few hours. Even if Venus is closer in distance, Mars is closer in terms of usable time. There is also the question of safety margins. Mars missions have benefited from decades of accumulated experience. Each mission builds on the last. Entry, descent, and landing systems are refined incrementally. Mistakes are analysed. Improvements are implemented. Venus missions have far fewer opportunities for iteration. Each mission must confront the same brutal conditions. Progress is slower not because of lack of interest, but because the environment limits experimentation. Orbital mechanics also affect human factors. A Mars mission involves long travel times, often 6 to 9 months each way. This introduces challenges related to radiation exposure, muscle loss, and psychological stress. These are serious concerns, but they are being actively studied on the International Space Station and through long-duration simulations. A Venus mission would involve shorter travel times, but the destination offers no relief. There is no extended surface stay, no opportunity to build routines, no gradual acclimation. The mission would be intense, compressed, and unforgiving. Humans tend to perform better when stress is distributed rather than concentrated. Mars allows stress to be spread out. Venus concentrates it. Fuel efficiency also intersects with payload planning. Mars missions can deliver heavy equipment designed for long-term use: habitats, power systems, rovers, scientific instruments. The expectation of longevity justifies the cost of transporting mass. Venus missions prioritize minimalism, lightweight, expendable systems. Every kilogram must justify itself within a narrow operational window. This difference shapes ambition. It is easier to imagine building something lasting when the math supports longevity. It is harder when every calculation points toward brevity. Even gravity assists, often used to optimize fuel use, tell a similar story. Spacecraft bound for the outer solar system frequently swing past Venus or Earth to gain speed. Venus often serves as a helper, a waypoint rather than a destination. Its gravity is useful, its surface is not. Mars, on the other hand, is not just a waypoint, it is an endpoint. The mathematics of orbits does not care about aesthetics or symbolism, it cares about energy, momentum, and timing. When those factors are combined with environmental realities, a pattern emerges that is hard to ignore. Mars sits at a point where orbital mechanics, fuel economics, and survivability align just enough to make sustained exploration plausible. Venus sits at a point where those same factors pull in different directions, closer but harsher, faster to reach but harder to stay, easier to fly by but difficult to inhabit. This is why discussions about Venus often focus on orbiters and atmospheric probes rather than landers and habitats. Orbit is a comfortable compromise. You can study Venus extensively without confronting its surface directly. You can learn from it without paying the full price. Mars does not offer that same buffer. To learn Mars deeply, you must engage with its surface, and because that engagement is survivable, even if difficult, it becomes worthwhile. Orbital math in this sense reinforces every other argument. It does not overturn the choice between Venus and Mars. It supports it quietly, adding numerical weight to what climate science and engineering already suggest. The path to Mars is longer in distance but smoother in effort. The path to Venus is shorter but steeper in consequence. As exploration planning continues, these calculations will only become more refined. New propulsion systems may shift the balance slightly. Advances in materials may expand what is possible, but the underlying geometry will remain. Space is not a straight line. It is a web of curves and compromises, and within that web, Mars occupies a position that allows human ambition to move forward step by step, rather than burning brightly and briefly before being forced to retreat. Long before anyone calculated trajectories or tested heat shields, Mars had already settled into the human mind as a place that felt reachable in a way few other worlds ever have. Not reachable in distance, or technology, or even survival. Reachable in imagination. That distinction matters more than it sounds, because imagination is where long projects are born and sustained. When people think about going to Mars, they are rarely thinking only about physics. They are thinking about what it would feel like to be there, to wake up under a pale sky, to look out across a horizon that is not Earth's but still reads as a horizon, to exist somewhere that is undeniably alien yet structured enough to feel navigable. Venus does not offer that feeling, Mars does. This is not a coincidence. It has everything to do with psychology, with how human brains process environments, threats, and the idea of endurance. Mars presents itself as hostile but legible. Venus presents itself as overwhelming and absolute. One invites preparation, the other discourages presence. Mars looks like a place you could struggle in. Venus looks like a place you would simply lose. That difference alone reshapes motivation. Human beings are remarkably adaptable, but that adaptability depends on feedback. We need to see cause and effect, effort and response, action and consequence. On Mars, this relationship exists. You insulate a habitat, it gets warmer. You shield against radiation, exposure drops. You plan for dust storms, systems ride them out. Progress is slow, but it accumulates. Venus disrupts this feedback loop. No matter how much effort you imagine applying, the environment dominates the outcome. The planet does not feel like it responds to intervention. It feels like it erases it. Psychologically, that is devastating. Mars also benefits from familiarity. Its surface is rocky. Its gravity pulls you down instead of crushing you or letting you drift. Its terrain has slopes, plains, ridges, and craters that the human visual system understands instinctively. Even its dangers feel recognizable. Cold, dust, thin air, radiation. These are extreme versions of things humans have encountered before. Venus's dangers are qualitatively different. Crushing pressure, heat that melts metals, acid clouds, a surface that cannot be reached safely and cannot be used. There is no everyday analogue, no ancestral memory to lean on, no evolutionary precedent. The human brain is not good at coping with environments that offer no reference points. Mars gives us reference points. This is why images of Mars are so powerful. Even grainy photos from early missions carried emotional weight. They showed rocks casting shadows, horizons fading into dusty distance, sunsets tinted blue by atmospheric scattering. These images did not look like paradise, but they looked like a place. People could imagine standing there. Venus's surface images when they arrived carried a different tone. They were fascinating but unsettling. The light was dim and yellow. The rocks looked crushed and baked. The sky pressed down visually as much as physically. The images did not invite presence. They warned against it. Mars also offers a sense of narrative continuity. When humans look at Mars, they see a story unfolding over time. A planet that was once warmer and wetter. A world that lost its magnetic field. An atmosphere that thinned. Water that disappeared. This narrative mirrors loss rather than excess. It feels tragic but comprehensible. Venus's story feels more abrupt. A world that crossed a threshold and became locked into an extreme state. The narrative feels less like decay and more like entrapment. Psychologically, loss invites repair. Entrapment invites avoidance. Mars also aligns with how humans perceive challenge. The obstacles on Mars feel difficult but solvable with enough preparation. You need protection from radiation. Build shielding. You need warmth. Insulate. You need water. Extract ice. You need air. Process carbon dioxide. Each problem maps to a solution. Venus's problems resist mapping, cooling, pressure, chemistry. Each solution generates new failures. There is no clear sequence of steps that leads from survival to comfort, or even from survival to stability. The absence of a clear path undermines commitment. This is especially important for long-duration missions. Astronauts are not just technicians. They are people who must live with uncertainty, isolation and risk for months or years. Their mental resilience depends heavily on the belief that their actions matter, that effort improves conditions. Mars supports that belief. Venus undermines it. There is also the question of control. On Mars, humans would be enclosed, protected and dependent on machines. But they would still have agency. They could move habitats, explore new areas, adjust systems, make decisions that affect their immediate environment. On Venus, especially in floating habitats, agency is constrained. You are at the mercy of atmospheric dynamics. You drift. You maintain altitude. You respond to forces rather than shaping them. Any major decision carries the weight of catastrophic failure. The sense of control is thinner. Humans tolerate danger better when they feel in control, even if that control is limited. This is why driving feels less stressful than being a passenger, even though it is objectively more dangerous. Mars lets us drive. Venus makes us passengers. Isolation also plays out differently. Mars is distant. Communication delays are real. Earth becomes a faint point of light. This creates psychological strain, but it also creates a sense of purpose. You are far away because you chose to be. You're there to do something specific. The distance feels earned. Venus is close, so close that Earth looms large. Communication delays are short, rescue feels almost imaginable, which paradoxically increases stress. You're not truly cut off, but you're still trapped in an environment that does not forgive mistakes. Closeness without safety creates a unique kind of tension. Mars's distance forces acceptance. Venus's proximity teases alternatives that cannot be reached. This distinction influences how people imagine themselves coping. Mars feels like exile with a mission. Venus feels like confinement without escape. There is also something important about time. Mars missions unfold slowly. Travel takes months. Surface operations stretch over years. Routines form. Days pass. The planet rotates on a cycle similar to Earth's. Astronauts would experience mornings, afternoons, evenings. This rhythm matters deeply to human psychology. Venus's day is profoundly alien. One Venusian day is longer than its year. The sun rises and sets at a pace that has no intuitive meaning. In floating habitats, artificial lighting would replace natural cycles entirely. Time would be imposed rather than experienced. Humans can live without sunlight, but not without rhythm. Artificial rhythms work best when they align loosely with natural ones. Mars offers that alignment. Venus does not. The colour of Mars also plays a subtle role. The planet's reddish tones are often described as harsh, but they are still part of the human visual palette. Earth has deserts. Earth has red rock landscapes. The hues feel extreme but not alien. Venus's palette, filtered through thick clouds and chemical haze, feels oppressive. Yellowish light, diffuse shadows, limited contrast. Psychologically, environments with low visual variation and constant brightness are associated with fatigue and disorientation. Mars gives variation. Venus compresses it. These factors accumulate. None of them alone determines planetary choice. Together, they create a psychological profile that either supports or resists long-term human presence. Mars emerges as the world where humans can imagine themselves adapting, learning, and eventually feeling competent, not comfortable. Competent. Competence is essential. People endure hardship better when they feel skilled rather than helpless. Mars allows skill to matter. Venus makes skill feel insufficient. This also explains why Mars has dominated fiction, art and cultural imagination for over a century. Stories shape expectations, and expectations shape motivation. Mars has been imagined as a place of struggle, discovery, and resilience. Even its fictional dangers often mirror real ones. Venus's fictional portrayals shifted dramatically once its true nature was revealed. It moved from jungles to infernos, from exploration to avoidance. Stories stopped placing people on its surface because it became psychologically implausible, not just physically dangerous. Cultural narratives feed back into real planning. When agencies propose missions, they rely on public support. Support is easier to sustain when people can picture success, even if that success is modest. A research station, a series of missions, incremental progress. Mars fits that image. Venus resists it. Even the language we use reflects this. We talk about going to Mars. We talk about studying Venus. The verbs matter. One implies presence, the other implies distance. This is not a failure of courage. It is an alignment of psychology with reality. Human exploration has always balanced bravery with caution. We cross oceans when we believe land exists on the other side. We hesitate when the sea looks endless and hostile without refuge. Mars looks like land. Venus looks like atmosphere. Few questions shape planetary exploration more deeply than this one. Are we alone? It sounds simple, almost childlike, but it quietly drives billions of dollars in funding, decades of mission planning, and generations of scientists who devote their lives to studying distant worlds. When we send machines across millions of kilometers of space, we are not just measuring rocks and gases. We are listening for something subtler, a chemical imbalance, a fossilized microbe, a whisper in the data that suggests biology once had a foothold somewhere else. and when the search narrows within our own solar system, two worlds consistently rise to the surface of that conversation: Mars and Venus. They sit close to Earth in cosmic terms, they are rocky, they share ingredients, and yet, when it comes to the search for life, they occupy very different positions. Mars is where we look for evidence of something that may have lived long ago. Venus is where we debate whether something could still be living now. That difference alone changes the tone of the search. Mars presents a story that feels familiar. Billions of years ago, it likely had liquid water flowing across its surface. River valleys carved into ancient terrain. Delta formations where sediment settled into basins. Minerals that only form in watery environments. The planet was not warm and ocean-covered like early Earth, but it was not the dry, frozen desert we see today. If life emerged on Earth under similar conditions, it is reasonable to ask whether it might also have emerged on Mars. This is why so many missions have focused on sedimentary rocks, dried lake beds, and ancient river channels. Rovers like Curiosity and Perseverance are not wandering randomly. They are deliberately exploring regions that once held water for extended periods. Water, after all, is the key solvent of life as we know it. When scientists analyse Martian samples, they are not looking for little green organisms waving from behind rocks. They are looking for biosignatures, chemical fingerprints, organic molecules arranged in patterns that are unlikely to arise through purely geological processes. So far, the evidence remains inconclusive. Organic molecules have been detected, ancient lake environments have been confirmed, but none of it definitively proves that life existed. The data is suggestive, not decisive. That ambiguity does not weaken the search, it strengthens it. Because Mars offers time. Even if life disappeared billions of years ago, the planet's cold, dry environment preserves evidence remarkably well. Without active plate tectonics to recycle crust, without constant resurfacing by lava, Mars acts like a geological archive. Layers remain intact. Ancient rocks are accessible. The past is not buried beneath molten transformation. Venus tells a different story. For a long time, Venus was dismissed in the search for life entirely. Its surface is far too hot. Its atmosphere is far too thick. Its pressure is far too crushing. Any life that might once have existed on the surface would have been sterilized long ago. But then attention shifted upward. At altitudes around 50 kilometers above Venus's surface, temperature and pressure are surprisingly moderate. Not Earth-like in every sense, but within a range that extremophile organisms on Earth can tolerate. In this narrow atmospheric band, droplets of sulfuric acid form clouds. The chemistry is hostile but not automatically fatal to all conceivable life. This led to a provocative idea. Could microbial life exist in the clouds of Venus? The hypothesis gained renewed attention when observation suggested the possible presence of phosphine gas in Venus's atmosphere. On Earth, phosphine is often associated with biological processes. Its detection on Venus was controversial and remains debated, but it reignited serious scientific discussion about atmospheric life. Even if phosphine proves to have a non-biological explanation, the mere fact that Venus's clouds remain chemically active makes them worth investigating. But here the paths diverge sharply. Searching for life on Mars means sending rovers, drilling into rocks, collecting samples, and perhaps one day returning them to Earth for analysis. These missions can last years. They can move carefully, methodically, accumulating evidence piece by piece. Searching for life in Venus's atmosphere requires entirely different strategies. Balloons or aerial probes must float within acidic clouds. Instruments must survive corrosive chemistry. Sampling must be rapid and precise. There is no surface base to support operations. Mars supports sustained searching. Venus demands brief forays. This affects confidence. On Mars, if you do not find evidence in one location, you can drive to another. You can refine your tools. You can update your methods. Exploration is iterative. On Venus, each mission must gather as much data as possible in limited time. Iteration is slower because operational windows are short and conditions are unforgiving. There is also the matter of preservation. If life once existed on Mars, fossilized remains might still be embedded in sediment. Chemical traces might linger in mineral matrices. Radiation damages organic molecules, but it does so slowly enough that some evidence could survive underground. On Venus, if life exists in the clouds, it would likely be active and fragile. Sampling it without destroying it becomes a delicate challenge. If life once existed on the surface, resurfacing events and extreme heat would likely have erased nearly all traces. Mars preserves, Venus transforms. From a psychological standpoint, this matters. The search for life requires patience. It requires the belief that evidence can endure long enough to be found. Mars offers that hope. Venus offers urgency. Urgency is exciting, but it is difficult to build long-term strategy around. There is also a philosophical dimension to this search. Finding life on Mars, even fossilized microbial life, would suggest that life emerges readily when conditions permit. Two neighbouring planets, both once wet, both developing life independently. That would profoundly reshape our understanding of biology's place in the universe. Finding life in the clouds of Venus would be equally transformative, but in a different way. It would suggest that life can adapt to extreme chemical environments, surviving not on solid ground but suspended in atmospheric droplets. Both discoveries would be revolutionary, but the path to them differs. Mars feels like a library waiting to be read. Venus feels like a fleeting signal waiting to be caught. This is not to say that Venus is ignored. Quite the opposite. Interest in Venus has resurged in recent years. Missions are being planned to study its atmosphere in greater detail. Orbiters will map its surface more precisely. Probes may descend through its clouds to sample chemistry directly. Yet even in this renewed focus, the expectations differ. Venus missions aim to understand climate evolution, atmospheric chemistry, and planetary extremes. Life is a possibility, but not the central pillar. Mars missions place life at the center of their objectives. This priority shapes budgets, timelines, and public imagination. People are drawn to the idea of life on Mars because it feels like a continuation of Earth's story. It feels like discovering a sibling that took a different path but once shared similar beginnings. Life in Venus's clouds feels more alien, more surprising, harder to integrate into existing narratives. That does not make it less important. It makes it less intuitive. When agencies choose where to send limited resources, they weigh probability, payoff, and feasibility. Mars scores highly on all three. Venus scores high on payoff, but lower on feasibility, at least in terms of sustained life detection missions. And so the search continues, tilted toward the red planet. Mars invites us to kneel beside ancient rocks and ask what they remember. Venus challenges us to dip instruments into acidic winds and ask what survives. Both questions matter, but one of them fits more naturally into a long-term plan that builds step by step, mission by mission, sample by sample. As the search for life expands beyond our solar system, the lessons learned from both worlds will shape how we interpret distant atmospheres and faint spectral lines. But for now, within our cosmic neighbourhood, Mars remains the quieter, more methodical candidate. Not because it guarantees discovery, but because it allows the search to continue without burning out quickly. And as attention shifts next toward technology, toward how we actually carry humans across interplanetary space, the presence or absence of life remains an undercurrent, reminding us that exploration is never just about reaching new ground, but about asking whether that ground once held something that looked back at the sky the way we do now. Before any rocket leaves the launch pad, before any rover unfolds its wheels or any astronaut straps into a capsule, there is a quieter reality that determines whether a mission ever happens at all. Money. Not in the abstract sense of ambition or inspiration, but in the concrete sense of budgets, votes, contracts, timelines, and trade-offs. Every kilogram launched into space represents years of engineering work, thousands of salaries, and the careful balancing of priorities against limited resources. Exploration is romantic in the sky, it is bureaucratic on the ground, and when planners evaluate where to send the next billion-dollar mission, cost becomes a deciding force. Mars and Venus are not equal in this equation. A mission to Mars is expensive, there's no way around that. Launch vehicles, deep space navigation, entry descent landing systems, surface operations, communication infrastructure, and years of mission control support add up quickly. Even robotic missions routinely cost hundreds of millions to several billions of dollars. Human missions multiply those costs dramatically. Life support systems, radiation shielding, redundancy, crew safety measures, return vehicles, training programs, and long-duration support all push budgets into territory that requires international cooperation and long-term political commitment. Venus missions are not cheap either. In fact, the hostile environment introduces additional engineering challenges that drive costs upward. Heat-resistant materials, reinforced pressure vessels, corrosion-resistant coatings, specialized electronics capable of operating at high temperatures, and mission designs that must survive extreme descent conditions all require custom solutions. But the real cost difference is not in the initial launch, it is in the return on investment. Mars missions can operate for years. Rovers like Opportunity and Curiosity dramatically exceeded their planned lifetimes. Orbiters continue transmitting data long after initial expectations. The longer a mission functions, the more data it returns, the more discoveries it enables, and the more justified its expense appears. Venus landers, by contrast, operate briefly. Even the most successful surface missions have survived only for short periods. Orbiters can last longer, but surface exploration remains constrained by heat and pressure. When operational windows are measured in hours rather than years, the cost per hour of data becomes extraordinarily high. Funding agencies notice that. There is also infrastructure to consider. Mars exploration has built an ecosystem. Orbiters relay data for rovers. Surface missions inform future landing site selection. Communication networks are established. Engineering lessons accumulate. Each mission builds on the previous one, reducing uncertainty and improving efficiency. This cumulative infrastructure lowers risk over time. Venus exploration lacks that same layered continuity. Missions are more isolated. The extreme environment limits iterative experimentation. Each new lander must essentially confront the same hostile baseline. The learning curve flattens quickly because physics does not change. Cost is not just measured in dollars, but in risk. Mars missions carry significant risk, but the environment allows for mitigation strategies. Landing systems have improved, redundancy has increased, technologies are refined incrementally. When something fails, engineers analyze the failure and adapt. Venus compresses risk into narrow margins. The environment allows little forgiveness. The probability of early failure remains high, which increases the perceived financial gamble. Governments and space agencies must justify expenditures to taxpayers and political leaders. They must demonstrate scientific return, technological advancement, and public engagement. Missions that offer sustained visibility and incremental progress are easier to defend. Mars provides that visibility. Each image from the surface, each drill core, each panorama of dusty hills, these become part of public imagination. They reinforce the sense that exploration is ongoing and productive. Venus, bright in the sky, remains distant in imagery. The few surface photos that exist are historically important, but they do not update year after year with fresh landscapes. Public engagement wanes when missions are brief and infrequent. Public enthusiasm influences budgets more than many scientists would like to admit. Human missions amplify cost differences dramatically. Sending humans to Mars is an enormous financial undertaking. likely requiring hundreds of billions of dollars over decades. Life support systems must operate autonomously for months during transit. Surface habitats must sustain crews for extended stays. Return vehicles must function reliably after months in harsh conditions. Yet even with those costs, the long-term vision includes sustainability, producing fuel on Mars, recycling water and air locally, growing food, building infrastructure that reduces reliance on Earth over time. These strategies aim to amortize cost across decades. A human mission to Venus's surface is currently beyond practical consideration, because survival time would be minimal. Floating atmospheric missions are theoretically more viable, but they introduce new layers of complexity. Continuous altitude control, corrosion-resistant materials, emergency escape systems capable of handling atmospheric instability. The cost would not only be high, but ongoing. Economic planning prefers projects with trajectories that trend towards stability rather than perpetual escalation. Mars missions can trend toward stability. Venus missions trend toward containment. There is also opportunity cost. Space agency budgets are finite. Funding one large project means not funding another. Every dollar directed toward a Venus lander is a dollar not directed toward Mars sample return, lunar infrastructure, asteroid mining research, or exoplanet telescopes. Decision makers weigh these trade-offs carefully. Mars sits at an intersection of goals. It supports planetary science, astrobiology, human exploration, technology development, and even geopolitical collaboration. It is versatile in its justification. Venus is scientifically crucial, especially for climate modelling and comparative planetology, but it does not intersect as cleanly with human exploration goals. Versatility increases funding resilience. Cost also interacts with timelines. Mars missions fit into multi-year planning cycles. Launch windows occur predictably. Infrastructure can be reused. Data pipelines remain active. Teams remain employed continuously, preserving expertise. Venus missions are more episodic. Long gaps between surface attempts reduce institutional continuity. Expertise must be rebuilt. Funding spikes and falls. Consistency lowers cost indirectly. There is another factor rarely discussed openly: failure tolerance. Mars missions can fail and still provide lessons that inform the next attempt. The public and policymakers often accept setbacks as part of a long-term effort. Venus missions, because they are rarer and more extreme, face heightened scrutiny. A single high-profile failure can discourage follow-up investment. Risk perception affects cost planning. Even private companies factor these realities into their ambitions. Commercial space ventures prioritize projects with scalable returns. Mars offers potential long-term presence. Venus does not yet present a similar economic narrative. This does not mean Venus lacks value. Scientific missions to Venus are underway and planned. Climate scientists, planetary geologists, and atmospheric physicists view Venus as essential to understanding planetary evolution. But when budgets tighten, priorities sharpen. Mars's alignment with long-term human presence gives it an advantage in funding debates. The cost of a mission is not simply the price of hardware. It is the cost of sustaining momentum. Mars sustains momentum because each mission feeds the next. Data accumulates, technologies improve, goals expand gradually rather than resetting. Venus resets frequently because the environment limits continuity. Even in public imagination, this difference resonates. People can picture a Mars base evolving over time. They struggle to picture a Venus base expanding beyond isolated floating habitats. Perception shapes policy. Ultimately, cost is about commitment. Nations commit to projects that promise durable returns: scientific, technological, cultural, or economic. Mars promises durability. Venus promises insight. Insight is invaluable, but durability anchors budgets. As exploration moves forward, costs will evolve. Reusable rockets reduce launch expenses. Advanced propulsion may shorten travel times. Material science may improve high-temperature tolerance. These advances could narrow the gap. But for now, the economic landscape reinforces every other factor we've examined. Environmental compatibility, psychological plausibility, orbital mechanics, and scientific continuity all converge with fiscal reality. Choosing where to go is never just about curiosity. It is about sustaining effort over decades without collapsing under financial strain. Mars fits within that framework. Set aside rockets, budgets, and habitats for a moment, and Venus stops being a destination question and becomes something more intimate. It becomes a mirror, not a flattering one, and not a perfect one, but close enough to make the reflection uncomfortable if you stare too long. Because Venus is not just a story about another planet. It is a story about how planets behave when certain balances are lost, and Earth, quietly and persistently, operates under many of the same physical rules. This is why scientists care so deeply about Venus, even though they have no plans to live there. Venus teaches us that climate is not a background condition. It is an active system. It responds to inputs. It amplifies feedback. And under the right circumstances, it can move into states that are stable, but profoundly hostile to life as we know it. One of the most important lessons Venus offers is that there is no guarantee of moderation. Earth feels stable because it has been stable for a very long time. Oceans have existed for billions of years. Temperatures have fluctuated, sometimes dramatically, but within bounds that allowed life to persist and diversify. This long-term stability can create the illusion that it is automatic, that it is somehow baked into being an Earth-sized planet at this distance from the Sun. Venus challenges that assumption directly. Here is a planet almost the same size as Earth, formed from similar material, orbiting the same star, and yet its climate followed a radically different trajectory, not because it violated physical laws, but because it obeyed them too well in a slightly different configuration. The key concept here is feedback. On Earth, feedbacks exist, but many of them are stabilizing. As temperatures rise, certain processes act to counteract that rise. Increased weathering pulls carbon dioxide out of the atmosphere. Oceans absorb heat. Clouds reflect sunlight. Over long timescales, plate tectonics recycle carbon between the surface and the interior, preventing runaway accumulation. These mechanisms do not make Earth immune to change, they make it resilient. Venus appears to have lacked enough of these stabilizers. Once water began to evaporate into the atmosphere in large quantities, it acted as a greenhouse gas, trapping more heat. More heat caused more evaporation. This positive feedback reinforced itself. At some point, the system crossed a threshold where stabilizing processes could no longer keep up. That threshold matters. Venus teaches us that climate systems can behave non-linearly. Small changes in input can produce disproportionately large changes in outcome once certain boundaries are crossed. The transition from warm to runaway is not gradual in human terms, it accelerates. This is not speculation. It is written into Venus's present state. Another lesson lies in permanence. Venus shows that climate change, once pushed far enough, can become effectively irreversible on timescales that matter to civilizations. The loss of water from Venus was not temporary. Hydrogen escaped into space. That water is gone forever. The planet cannot simply cool down and regain its oceans. Earth's water is protected by gravity and a magnetic field that reduces atmospheric loss. But Venus reminds us that not all losses are recoverable. Some changes close doors permanently. This shifts how scientists think about risk. It is not only the magnitude of change that matters, but whether that change pushes a system into a new basin of stability. Once there, returning to the previous state may require forces far beyond what natural processes or intelligent intervention can supply. Venus also reframes how we think about carbon dioxide. On Earth, carbon dioxide is a trace gas. It represents a small fraction of the atmosphere, yet it plays an outsized role in regulating temperature. On Venus, carbon dioxide is the atmosphere. Its dominance is total. This contrast illustrates something crucial. Greenhouse gases do not need to be abundant to matter. Their effect scales with feedback, not just concentration. Venus's atmosphere is an extreme case, but it demonstrates the end state of a process that begins subtly. Importantly, Venus does not suggest that Earth is destined to become Venus. The differences between the two planets are significant. Earth has oceans that absorb heat and CO2. Earth has plate tectonics that cycle carbon. Earth has a stronger magnetic field. Earth receives less solar energy. But Venus shows that the presence of stabilizing mechanisms is not the same as a guarantee they cannot be overwhelmed. Another lesson Venus teaches us is about timescale mismatch. Human decision-making operates on years, decades, maybe centuries. Planetary systems operate on thousands to millions of years. Venus's transformation unfolded over immense spans of time, likely faster than geological intuition might expect, but still far slower than human lifetimes. This creates a dangerous blind spot. Processes that are slow on human timescales can still be fast on planetary ones. By the time changes become obvious to a civilization, momentum may already be built into the system. Venus did not flip overnight. But once it began to accelerate, there was no human-scale moment where someone could have intervened and reversed course. That realization carries weight. Venus also teaches us humility about prediction. For a long time, Venus was misunderstood. Early scientists underestimated its temperature. Some believed its clouds hid oceans. Even with improving data, interpretations lagged behind reality. The planet resisted simple classification. This is a reminder that complex systems often behave in ways that challenge intuition. Climate models improve, but uncertainty remains. Venus encourages caution in assuming we fully understand every interaction within a planetary system. It also emphasizes the importance of comparative planetology. We understand Earth better because we can compare it to Venus and Mars. Each planet represents a different outcome from a similar starting point. Earth sits between two extremes, not just in distance from the Sun, but in climate behavior. Mars lost much of its atmosphere and became cold and dry. Venus retained and amplified its atmosphere and became hot and crushing. Earth retained enough atmosphere to stay warm, but not enough to overheat. This trio forms a natural experiment. Without Venus, Earth's climate might seem inevitable. With Venus, it becomes contingent. Another subtle lesson Venus offers concerns inertia. Venus's atmosphere is massive. Once heated, it retains energy efficiently. This creates thermal inertia, meaning changes propagate slowly but persist strongly. Once the planet reached its current state, it stayed there. Earth's climate also has inertia, though less extreme. Oceans store heat. Ice reflects sunlight. Changes introduced today can echo far into the future. Venus reminds us that climate does not respond instantly to intervention. Reducing inputs does not immediately restore previous conditions. Systems take time to respond, and that time lag can obscure cause and effect. This is why Venus is often invoked not as a prophecy, but as a boundary condition. It defines what happens when certain limits are exceeded. It tells us where the cliff edge is, even if Earth is not standing right at it. There is also a lesson about energy balance. Venus receives more solar energy than Earth, but not dramatically more. The difference alone does not explain the temperature disparity. The key is how that energy is processed. Energy in, energy out. Venus's atmosphere traps outgoing infrared radiation so efficiently that equilibrium occurs at a much higher temperature. Earth's atmosphere allows enough energy to escape to maintain moderate conditions. This reinforces a critical point. Climate is not just about how much energy arrives, but about how easily energy leaves. That insight applies universally from planets to buildings to ecosystems. Venus also teaches us that beauty can be deceptive. From Earth, Venus is luminous. elegant, serene. Its appearance gives no hint of its hostility. This disconnect between appearance and reality is not just poetic. It is instructive. Systems can look stable until they are not. Venus's clouds look calm. They hide turbulence, superrotation, and chemical aggression. Earth systems can also appear stable while undergoing subtle shifts beneath the surface. The lesson is not fear, it is attention. Another important takeaway concerns irreversibility and ethics. If Venus once had oceans and possibly habitable conditions, then its transformation represents the permanent loss of a potentially life-supporting environment. This invites uncomfortable questions about planetary stewardship. Earth is currently the only known world that supports complex life. If certain changes are irreversible, then preventing them becomes far more important than attempting to fix them later. Venus underscores that prevention is cheaper, easier, and more reliable than repair. It also informs how we think about exoplanets. As astronomers discover thousands of planets around other stars, many fall into categories that resemble Venus more than Earth. They are Earth-sized, close to their stars, with thick atmospheres. Without Venus as a reference, these worlds might be misclassified as potentially habitable. Venus sharpens our criteria. It tells us that size and location are not enough. Atmosphere matters, feedback matters, history matters. In that sense, Venus improves our ability to find Earth-like worlds by showing us what Earth-like is not. There is a final lesson that is less scientific and more philosophical. Venus reminds us that not every world exists for us. Some worlds exist to be understood, not inhabited. Their value lies in what they reveal, not in what they offer as homes. This distinction matters as humanity extends its reach. Exploration is not always about settlement. Sometimes it is about restraint, about learning from difference rather than trying to erase it. Venus teaches Earth by contrast. It shows us how fragile the conditions for life can be, how narrow the range of long-term habitability may be, and how easily similarity can diverge into extremes. Mars teaches us about loss. Venus teaches us about excess. Earth sits between them, balanced not by destiny, but by circumstance. That realization deepens the question of why we go where we go. We are not just choosing destinations, we are choosing which lessons to prioritize. Mars offers lessons about survival, resilience, and rebuilding. Venus offers lessons about limits, thresholds, and consequences. Both are necessary. But only one aligns easily with the human desire to stay. Looking ahead, exploration stops being a question of which planet is closer and becomes a question of how humanity chooses to move forward at all. Not just outward, but deliberately, carefully, with an awareness that every destination shapes the technologies we build, the risks we normalize, and the stories we tell ourselves about what progress means. The future of exploration is not a single path. It is a branching set of priorities, each pulling resources, attention, and imagination in different directions. Mars and Venus both sit within that future, but they occupy very different roles, and those roles are becoming clearer with time rather than more ambiguous. Mars is increasingly treated as a proving ground, not a paradise, not a backup Earth, but a place where humanity can test its ability to function beyond its home world without immediately confronting environments that overwhelm every margin. The emphasis is shifting from symbolic achievement to operational endurance, staying longer, fixing problems locally, reducing dependence on constant resupply, learning how to exist somewhere that does not naturally support us, but does not actively erase us either. This shift is subtle, but important. Early space exploration focused on firsts, first orbit, first landing, first footprint. These milestones mattered because they demonstrated capability. But capability without continuity fades quickly. The future demands something different, persistence. Mars aligns well with that demand. Planned missions increasingly emphasize infrastructure rather than spectacle. surface power systems that last for decades, habitats designed for repair rather than replacement, supply chains that rely on local materials, communication networks that function as permanent extensions of Earth-based systems rather than temporary links. These are not glamorous goals, but they are transformative. They mark the transition from visiting to inhabiting. Venus, by contrast, occupies a different future role. It is becoming a focal point for understanding extremes rather than extending presence. Missions planned for Venus emphasize orbiters, atmospheric probes, and short-duration descent vehicles. The goal is to extract information, not to establish footholds. This does not make Venus less important. It makes it more precise in its purpose. Venus is where exploration refines theory. Mars is where exploration tests practice. Both are necessary, but they require different mindsets. The future also brings changes in technology that will influence how these worlds are approached. Advances in propulsion, material science, robotics, and artificial intelligence are reshaping what is feasible. Faster transit times reduce radiation exposure and psychological strain. Smarter autonomous systems reduce reliance on real-time human control. New alloys and electronics extend operational lifetimes in harsh environments. These advances benefit Mars and Venus differently. On Mars, improved autonomy allows rovers and habitats to operate more independently, adapting to dust storms, temperature swings, and unexpected failures. On Venus, autonomy is essential simply to function at all, but it does not change the underlying limits imposed by heat and pressure. This asymmetry persists even as technology advances. There is also a growing recognition that exploration does not have to be human-centered to be meaningful. Robotic missions are becoming more capable, more flexible, and more scientifically productive. They do not require life support. They do not suffer from radiation exposure or isolation. They can operate in environments humans cannot. Venus benefits greatly from this trend. High-altitude balloons, long-duration atmospheric platforms, and orbiters equipped with advanced sensors can study Venus continuously without confronting its surface directly. These missions promise to answer long-standing questions about atmospheric dynamics, volcanic activity, and climate evolution. Mars also benefits, but in a complementary way. Robots prepare the ground, they scout locations, they test technologies, they gather data that informs human planning. Rather than replacing humans, they extend them. The future of exploration increasingly looks like a partnership between human and machine, each going where the other cannot. Mars sits at the intersection of that partnership. Another major shift shaping the future is international collaboration. Large-scale exploration is no longer the domain of a single nation. Costs are too high, timelines are too long, expertise is too distributed. Mars missions increasingly involve cooperation between space agencies, shared data, and coordinated planning. This trend favours destinations that support long-term shared goals. Mars fits that framework. It offers scientific return, technological development, and symbolic value that can be distributed across nations. Joint missions make sense when infrastructure persists and knowledge accumulates. Venus missions, while collaborative, are more episodic. They do not anchor long-term multinational presence in the same way. There is also the question of commercial involvement. Private companies are investing heavily in launch capabilities, spacecraft design, and mission support. Their motivations vary, but sustainability matters. Commercial actors look for pathways that lead to repeated use, scalability, and eventual economic return. Mars, again, aligns more naturally with these criteria. Concepts like in situ, resource utilization, surface construction, and long-duration operations create opportunities for services, logistics, and innovation. Venus, with its extreme constraints, offers fewer near-term commercial incentives. This does not mean Venus will be ignored. It means it will be approached primarily through public scientific missions rather than mixed public-private ventures. the future also brings ethical questions that are becoming harder to avoid. As exploration extends beyond observation toward intervention, humanity must decide how much it should alter other worlds. Terraforming discussions raise concerns about planetary protection, preservation of potential biosignatures, and the moral implications of reshaping environments that may have intrinsic value beyond human use. Mars sits at the center of these debates. If microbial life once existed there, or still exists underground, how do we balance the desire to explore and settle with the responsibility to avoid contamination? If Mars is lifeless, does that grant permission to alter it freely, or does it still deserve preservation as a natural record? Venus raises similar questions in different ways. If life exists in its clouds, how do we study it without disrupting it? How do we protect environments we cannot inhabit but still influence through our instruments? The future of exploration is not just technological, it is philosophical. Another emerging theme is resilience. Earth is increasingly recognized as fragile. Climate change, biodiversity loss, and resource depletion have sharpened awareness that planetary systems can be stressed beyond comfort. This awareness drives interest in space not as escape, but as perspective. Mars offers a lens on planetary decline, a world that lost much of what made it habitable. Venus offers a lens on runaway excess, a world that crossed thresholds and never returned. Together they inform how humanity thinks about stewardship. Future exploration may prioritize understanding these planetary endpoints not to replicate them, but to avoid them. Missions to Venus become critical for refining climate models. Missions to Mars become critical for understanding loss of atmosphere and magnetic protection. The future is not about choosing one planet over another forever. It is about assigning roles. Mars as a testbed for presence, Venus as a benchmark for limits. There is also a temporal shift underway. Exploration planning is extending further into the future than ever before. Agencies are no longer thinking in terms of single missions, but of multi-decade arcs. Lunar infrastructure feeds Mars missions. Mars experience feeds deeper space exploration. Each step builds on the previous one. Venus fits into this arc as a parallel thread rather than a stepping stone. Knowledge gained there informs exoplanet studies and climate science, rather than serving as a rehearsal for human settlement. This division of roles may become more explicit over time. Public perception will play a role as well. As images from Mars continue to arrive, as sample return missions bring pieces of another world back to Earth, the sense of connection will deepen. Mars will feel less abstract, more real, more present. Venus will remain distant, luminous, intellectually compelling, but emotionally remote. That distance does not reduce its importance, it clarifies it. Another factor shaping the future is adaptability to uncertainty. Mars exploration benefits from uncertainty. Unknowns drive missions. Each discovery opens new questions. The planet reveals itself slowly, inviting continued investigation. Venus presents uncertainty too, but of a different kind. The broad strokes are already known. Extreme heat, crushing pressure, runaway greenhouse. The questions are more detailed, more specialized, important, but less expansive. This influences narrative momentum. Stories thrive on unfolding complexity. Mars offers that. Venus offers resolution. As exploration continues, attention will also shift outward beyond these two planets. Moons like Europa and Enceladus, with subsurface oceans, are already drawing intense interest. Titan, with its complex chemistry, offers another path entirely. Asteroids present resource opportunities. The outer solar system beckons. Mars remains central because it sits between Earth and these more distant destinations. It is a bridge, a place to learn how to operate away from Earth without committing to environments that overwhelm. Venus does not occupy that bridging role. In the long view, this may be Venus's greatest contribution. By being so clearly unsuitable for human presence, it sharpens criteria. It forces clarity. It prevents romanticism from drifting too far from reality. The future of exploration will likely involve more restraint than past eras imagined, more careful selection of targets, more emphasis on sustainability, more respect for planetary systems as they are rather than as blank slates. Mars fits within that more cautious ambition. Venus stands as a reminder of what happens when systems tip beyond control. As technology advances, as generations change, and as humanity's relationship with Earth evolves, these roles may shift slightly, but the underlying logic remains. Exploration moves where effort compounds rather than evaporates. Mars allows compounding, Venus resists it. The future will not abandon Venus, nor will it rush blindly toward Mars. It will continue to differentiate between learning and living, between observing and inhabiting, between what can be studied and what can be sustained. And in that differentiation, the question that began this journey quietly answers itself, not through preference or proximity, but through alignment with long-term possibility. The future of exploration is not about chasing the nearest world. It is about choosing the ones that let us stay long enough to understand what we are becoming as we leave home behind, step by careful step, without assuming that every bright light in the sky is meant to be followed, or that every destination is asking to be occupied rather than simply understood. Distance, in the end, turns out to be a misleading way to think about the future. We grow up learning that closer means easier, that the nearest option is usually the most practical one, that effort increases steadily as distance grows. On Earth, that intuition works well enough. In space, it quietly falls apart. Venus is closer, brighter, more obvious. And yet Mars, colder and farther away, is the world we keep preparing ourselves to meet. Not because we overlooked Venus, because distance was never the real barrier. What matters, once you look closely, is how a world responds to being approached. Whether it gives you time, whether it allows adjustment, whether it tolerates mistakes long enough for learning to take place. These qualities do not show up on maps. They are not visible in the night sky. They only reveal themselves when physics, biology, engineering, psychology and patience are all considered together. Venus teaches this lesson without compromise. From Earth, Venus feels almost intimate. It appears regularly, faithfully, glowing in the same sky we use to navigate our own lives. It rises before workdays begin. It lingers after evenings wind down. For centuries it felt like a companion to human timekeeping. That familiarity creates a quiet expectation. Surely the nearest neighbour would be the first one we truly visit, yet familiarity is not the same as compatibility. Venus is a world that does not negotiate. Its atmosphere does not offer gradual thresholds. Its climate does not oscillate gently. Its surface does not wait. The planet reached a state of equilibrium long ago, and that equilibrium excludes us. It is stable, but stability is not kindness. Mars, by contrast, is unsettled. Not chaotic, but incomplete. Its atmosphere is thin, its climate is fragile, its history reads like an unfinished sentence rather than a conclusion. That incompleteness creates space for effort to matter. Mars allows intervention without immediate erasure. It allows tools to function long enough to be repaired. It allows humans to imagine adapting rather than merely enduring. This difference reshapes how destiny is formed. Destiny is often mistaken for inevitability, but in exploration, destiny is something that emerges from alignment. A place becomes a destination not because it is close, or bright, or obvious, but because it aligns with what a species can realistically do over time. Mars aligns with endurance, Venus aligns with warning. That does not diminish Venus's importance. In many ways, Venus may be the most important planet in the solar system after Earth, precisely because it shows us what happens when balance is lost and cannot be recovered on any timescale that matters to civilizations. It offers clarity rather than comfort. It reminds us that not all paths are reversible, and not all similarities lead to shared futures. Venus tells us that planets have thresholds. Mars tells us that planets can fade without collapsing entirely. Earth exists between them, not as a guaranteed success story, but as a temporary outcome maintained by ongoing balance. Understanding this changes how exploration feels. Going to Mars is not about escaping Earth. It is not about abandoning responsibility. It is about learning what happens when you try to sustain life in a place that does not offer it freely. It is about practicing care under constraint. Mars does not welcome us. It tolerates us conditionally. That conditional tolerance is invaluable because it mirrors the reality we face at home. Venus offers a different mirror. It shows what happens when conditions tip too far. When feedback overwhelms regulation. When energy cannot escape. When repair is no longer an option. Venus does not threaten Earth as a destiny. It contextualizes it as a possibility. Distance, then, is not destiny. Feedback is. Thresholds are. Systems are. The reason we are not going to Venus in the same way we are going to Mars is not a failure of ambition. It is an expression of maturity. Early exploration was driven by firsts and flags. The next phase is driven by continuity, by choosing environments where presence can be sustained long enough to learn something meaningful. Mars allows continuity. Venus does not. That distinction will matter more, not less, as exploration extends outward. Beyond Mars lie worlds far stranger than either Venus or the Red Planet. Moons with subsurface oceans, planets locked to their stars, atmospheres thicker or thinner than anything we have encountered. Many of these places will resemble Venus more than Mars. They will be extreme, stable, and resistant to intervention. Venus prepares us for that reality. It tells us that some worlds are not destinations but references. They define the edges of what is possible, so that we can recognize the narrow corridors where life can persist without constant catastrophe. Mars occupies one of those corridors. It is not generous, it is not forgiving, but it is not final. That quality makes all the difference. Human exploration at its best has never been about conquering environments. It has been about learning to live within limits. Early humans did not dominate deserts or tundra by overpowering them. They adapted slowly. They learned rhythms. They accepted constraints. They built cultures around survival rather than denial. Mars asks for that same humility. Venus refuses it because humility is not enough there. The environment demands transformation on a scale we cannot yet offer, and until that changes, if it ever does, Venus will remain a place we study rather than settle, admire rather than approach, learn from rather than inhabit. There is also something quietly reassuring in this. It means the universe is not arranged conveniently for us. It means proximity does not guarantee suitability. It means bright lights are not invitations by default. These are healthy lessons for a species just beginning to extend itself beyond its homeworld. They encourage discernment. They slow reckless ambition. They force questions that have no easy answers. Why go somewhere at all? What are we hoping to learn? What are we prepared to risk? And what are we willing to accept as limits rather than challenges to be overcome? Mars and Venus sit close together in space, but far apart in what they demand from us. One asks for patience and persistence. The other asks for understanding and restraint. Both are valuable. Both shape the future in different ways. As exploration continues, the line between studying and settling will become more important. Some worlds will teach us by allowing us to stay. Others will teach us by refusing us entry. Neither role is superior. They are complementary. Venus teaches Earth how climates fail. Mars teaches Earth how worlds lose protection. Earth teaches us how narrow the path between those outcomes really is. That context changes the meaning of going to Mars. It is not about choosing one planet over another, as if the decision were a preference. It is about choosing the kind of relationship we can sustain with a world beyond Earth. Mars allows a relationship built on effort, repair, and learning. Venus allows a relationship built on observation, humility, and caution. Distance is not destiny, because destiny is not fixed by position alone. It is shaped by interaction, by response, by whether a place lets you stay long enough to change yourself without having to change the planet first. Mars lets us try. Venus tells us to listen. And perhaps the most important outcome of this comparison is not where we go next, but how we think about going at all. With less assumption. With more respect for systems larger than ourselves. With an understanding that some frontiers are meant to be crossed and others are meant to be understood from just far enough away. As you sit wherever you are right now, under a sky that still belongs to Earth, Venus may be rising or setting. Mars may be invisible, lost among distant stars. The closer world shines brighter. The farther one waits quietly. And in that contrast, the answer settles gently, not as a conclusion, but as an orientation. We are not choosing Mars because it is farther. We are choosing it because it gives us time. Time to learn. Time to adapt. Time to discover what kind of explorers we actually are before distance becomes destiny somewhere else. And the choices we make can no longer be revised.